Okay, great. So welcome everyone to this next day of the school. We're very lucky to have Kostas Papagiorgakis from Queen Mary University in London. And Kostas is giving a pedagogical lecture now. So as a request to all of the students, if you have any questions, whatever question you have, you should stop Kostas and ask him. So I think that he would enjoy your interaction, and he designed this specifically for the students. So please stop him if you have any questions. Kostas will be telling us about deep finite temperature bootstrap, and this will be his first lecture. Go ahead.
Great, thank you, Robert. So thank you very much for the invitation. Thank you for, it's my first time in South Africa. It's a beautiful place. I'm very happy to be giving these talks for you. So I interpreted Anosh's brief extremely literally. He said there's going to be a research talk which is targeted to people in the field, and then I would like you to give two pedagogical talks targeted at masters and PhD students who are not working on the field, in order for them to be able to follow the research talk. So I'm going to start today. This morning is part one of the pedagogical talk, and then the last day talk of the day is going to be the second part, and I will explain some of the words that appear in this time. So in the first part, I'm going to focus entirely on the bootstrap and the conformal bootstrap. And I'm not going to assume any familiarity at all with CFTs or the bootstrap program. So it's going to be very, very basic, starting from the ground up, working up to the derivation of the bootstrap equations and what it conventionally, sort of how it is approached numerically. Later on today, I will focus on the finite temperature modifications to the bootstrap program for CFTs, how things become a little bit different in that case. And then part two of the second lecture is going to be some introductory information about deep neural networks, which I will be using tomorrow to apply this framework to the bootstrap of finite temperature CFTs. One of the things that I've done, and if I can ask the technical team in the back who are not paying attention to me right now, excuse me, can we have the first slide if possible? So I prepared some lecture notes, which I have here. They include everything that I'm going to be talking about. In fact, probably I'm not going to have the time to go over everything here. If you'd like to take a photo of this QR code, you'll just get the lecture notes directly onto your phones. You can forward them to yourselves, etc. And towards the end, I also give some steps about how you can go from what I'm going to be saying in the pedagogical lecture notes to the full technical talk tomorrow. So let's start with some introduction. And the first thing is why I'm interested in conformal field theory. So conformal field theories, as we'll discuss, are very special theories in the space of QFTs, and they appear in the study of critical systems. They appear in the study of string theory, as you have probably already seen, and importantly, in the context of this workshop, in the study of ADS-CFT, right, where they capture the gravitational dynamics of a theory in D+1 dimensions, living on the D-dimensional boundary of that space. So what makes them very special is that they enjoy a large amount of symmetry. You know probably from your study so far that the more constrained a theory is, the easier it is to try and solve. And in this particular case, CFTs are actually quite powerful because you can apply certain techniques which are entirely non-perturbative. So you do not need a Lagrangian, a perturbative expansion necessarily. I mean, you can have that as well to define them and work with them. And the bootstrap program is exactly one of these approaches. So let's move on a little bit to I'm going to have problems with my pens. I can anticipate that already. With the formal group. So the conformal group is a group of transformations which kind of enhances the Lorentz transformations that you know. It includes translations. So you have x mu being translated to x mu plus, I don't know, alpha mu. This has a corresponding generator of translations in mu, which is going to be important. We have rotations. Can people see right here? I mean, yeah, you guys can. Yeah, on that, yeah, that's fine, great. So, so you have that. And there's a corresponding generator, mu nu. Okay, so these are the standard I'm talking about CFTs here in Euclidean signature, so everything is Euclidean. There's no time direction. There is also a dilatation, there's a scaling. So x mu goes to lambda x mu. The corresponding operator is the dilatation operator d, which scales things up and down. And I would like here my lambda to be positive. And I have something known as a special conformal transformation. XFM is shorthand for transformations. Special conformal transformations are a bit more complicated. Let's write them down. You can understand them as an inversion transformation, or x goes to 1 over x, followed by translation and followed by another conversion. And has a corresponding generator in mu. So my generators, translations, rotations, dilatations, and special conformal transformations close into something that is known as the conformal algebra. And I have given explicitly questions. Ask me. Don't be shy. Ask me.
No, I was asking, is it, well, it has the same transformation as the Poincare group.
It includes the Poincare, correct? It's an extension.
It includes.
Exactly. Ask this question. Don't ask him. Ask me. Yeah. Excellent. Very good. So as you said, these two guys are the Poincare rings extended by the dilatations and the special conformal transformations. So all these generators close into the conformal algebra. If you guys take a look at the notes, I've given you all the equations, all the commutation relations between these generators, right? That gives you the conformal algebra in Euclidean signature. Wonderful. So you probably know, if you've taken a CFT string theory course, that when the space-time dimension is 2, this is a very big symmetry, right? It's infinite dimensional. It's the Virasoro symmetry. But what I would like to focus on here is instead be greater than 2, and focus with this part, the so-called global part of the conformal symmetry that you probably know from CFT in 2 dimensions. Very good. So now that we know the symmetries that define my conformal theory, I would like to see how that helps us organize the spectrum of operators in a given theory. So the key objects in a CFT are local operators and their correlation functions. So Jinan is talking about extended operators and defects, but which is a very important part of the theory, but I'm going to focus only on the local operator spectrum of my CFT. And how are these guys characterized? You can characterize them by their conformal dimension. So if you perform a scaling transformation with of this type, you get that your operators pick up a multiplicative factor lambda minus delta x, and this thing here is the conformal dimension of the scaling dimension. My operator. Okay, so this is one of the things that characterizes my operator. The other thing is the spin of the operator, which I will denote by capital J. So this is the SOD representation, the representation under which these local operators transform under the action of rotations. Very good. So I can do more, however. I can use some properties of the transformations of the operators under the special conformal transformations to have a set of special operators characterizing my spectrum. So it turns out that there is something known as a primary operator. So primary operators are operators that get annihilated by the action of the special conformal generators. Okay, so here, the action, because we're talking about operators, right? The action of these generators is an adjoint action. And because these guys, if this was not introduced at the origin of my space-time, I would have some action of k mu on the positions. The cleanest way of writing these things is to just introduce the operator exactly at the origin. Okay. So operators that obey this are called primary operators. And then I can construct a whole infinite tower of so-called descendant operators. Descendants by acting with derivatives, and on my primary. So this is a so-called conformal descendants. These operators here, let's say that this operator has dimension, what do I call it here? Delta, that has dimension delta. Then the whole tower of descendants have dimension, which is delta plus n. So each time you have a derivative acting, which is generating translations, is generated by p mu. Each time I have a derivative acting on this primary operator, I increase the scaling dimension of the corresponding operator by 1 unit. Okay, so the primary, along with the tower of descendants, is collectively known as a conformal family. And this is because this includes an infinite number of operators, it's a very neat way of organizing the spectrum of my theory.
So spin of the operators?
The spin as well, I mean, the increases as well, depending on the contractions of. Okay.
We have, say, equation of motion.
Yeah. Yeah. So, depending on, if it's a free field, for example, you have to do this operator is identically zero. It's a null state, and you have to kind of protect it up. Great. So now let's go even more specific and special. So if you're interested in unitary theories, so for unitary theories, you would like the spectrum of your operators your Hilbert space has to be positive definite, and there are some corresponding bounds on the dimensions of operators that arise from that requirement. So the scaling dimensions are bound to be greater or equal to d minus 2 over 2. This is when your spin is 0. Scalars. And for spins higher than 0, or anything else, it's d plus j minus 2. J is greater or equal to 1. Yeah, so this is a unitarity bound. If you don't want negative norm states in your Hilbert space, you have to have conformal dimensions that start from these cases. If you saturate this bound, so when this thing is an equality, you have free fields in the case of scalars, and then you have sort of high spin currents when j is greater than 1, conserved currents. Very good. So now that we've set up conformal symmetry, how we characterize the operator spectrum, let's see what are the observables of my theory. So in this, for CFTs, because you cannot define asymptotic states, sort of conformal transformations map things from infinity to finite distances in your space. The observables are correlation functions of operators. So ideally, what you would like to do is to be able to have the power of computing any correlation function that someone gives you. That would mean that you've solved the theory. So what is the simplest thing that you can imagine is the expectation value of some operator. In fact, from now on, I'm going to be simplifying my life and deal only with scalar operators. So the expectation value of any operator in your theory, the 1-point function is 0, because the correlation functions have to obey the conformal symmetries, and there's no way to ensure the conformal that this thing is invariant in conformal transformations unless it is zero. So for example, this carries a scale. This thing does not carry a scale. So this kind of automatically sets it to zero. Okay, so there's no information here. Let's go 1 point higher. So it turns out that the 2-point function of some operators in your theory is completely fixed by the requirement that this 2-point function is invariant under conformal transformations up to a normalization C0 and some factor in the denominator that depends on the insertion of this guy and is raised to the power of 2 times the dimension of this operator. So the thing that I would like to bring your attention to here is that the dimension of these 2 operators has to be equal for this 2-point function to be non-trivial. Otherwise, if delta is not the same, these are not the same dimensions, this 2-point function is identically 0. So there's not a lot of information in the 2-point function either, except for how you normalize your operators. Okay. Let's go 1 point higher and see what happens in that case. So now if you go to 3-point functions, let's return to scalars. Then conformal symmetry once again fixes the form of the 3-point function almost entirely up to a constant. There is a complicated denominator, but it's got some reasonable structure. X1, 2, X2, 3. This is what conformal invariance fixes this 3-point function to be.
So,
yeah,
silly question.
Please, anything.
What's the difference between the scalars now, the phi's and the o's?
So here I'm talking, I would like to discuss this in all generality for the 2-point function. So there is kind of, there's a diagonal in space of operators, and now kind of reverted back to working with scalars so that I don't have any issues with that.
And now this 3-point function, so x1, and then the other two.
I'm about to define this. So xij is defined as xi minus xj.
Okay, but phi 2 and phi 3, they're both evaluated.
Thank you. Thank you very much.
Well, there's no reason why the dimensions have to match.
Conformal invariance is the reason.
Well, for the 3-point.
Here, now they don't have to be the same. For the 2-point function, they have to be the same. But for the 3-point function, you can have things with different dimensions and get a non-zero answer. Yeah, I'm using here scalars because it's the easiest thing to do. If I had fields which were not scalar, then you start having sort of Lorentz indices, and then you have to match that Lorentz index structure on the right-hand side, and it's going to be ugly. There are expressions like that you can find and write down explicitly. Yeah. So here is for everything. Here I'm just simplifying. Say it again. Here is for any operator. In this case, I'm just simplifying. It's again for any operator, but it is non-zero, even if you have operators that are not the same. Great. Now, what is the non-trivial information in this 3-point function? The non-trivial information is this guy over here. These things are called the 3-point function coefficients. And you can think of them loosely as the structure constants of your CFT. They are the only things that contain dynamical information about your theory. So everything else is constrained by conformal symmetry. And this is the first place where, for example, theories with the same spectrum are different. So if they have different 3-point function coefficients, they encode different dynamics. Okay, so they're important, very important quantities. Great. Let me just say this encode dynamical data.
So the F1, 2, 3, does that depend only on the space-time points?
Good. It does not. It's a constant. It depends on. It's a number. It's not a function. The space-time dependence is taken care of by this denominator. Yeah.
They would change as your operators change, right? The Fs.
This thing changes the operator change. The only dependence on what operator you're dealing with comes from the exponents and the conformal dimensions corresponding to the operator. So in fact here, yes, good. This is a bit of a silly way of writing things. Okay, thank you. Maybe this is a typo. Maybe I should have kept this as an O and assume that they're all scalars, but they can have different conformal dimensions. And O1, O2, O3. Because if I write it 5, 5, 5, then delta 1, delta 2, and delta 3 are all the same. So okay, this is a typo. And in that case, you just have x1, 2 to the power of delta, etc. So let's say that these are scalars, the dimensions of which are delta 1, delta 2, delta 3. In that case, this equation is the correct equation.
So if you had O4, O5, O6, then that would be some different number, right?
Yeah.
Okay.
Okay, so 1-point functions, 0. Any point function, 0. 1-point function, 2-point functions, completely determined up to the normalization of the operators. I can normalize this thing to be 1 by dividing my operator with square root of CO. 3-point functions, now there's something interesting happening. The space-time dependence is completely encoded up to a constant that encodes the dynamics of my theory. Let's go now 1 point higher and see what happens. What about 4-point functions? So before I talk about 4-point functions, I would like to introduce something known as the conformal cross ratios. So the conformal cross ratios are a combination of the space-time points or the differences. X1, 2 squared, x3, 4 squared, x1, 3 squared, x2, 4 squared. This is this parameter called u, and here this is so this is multiplicative, and then I have a parameter v, which is a similar combination, x1, 4 squared, x3 squared, x1, 3 squared, x2, 4 squared. What is special about these cross ratios, the ratios of these differences of squares of difference of your space-time points, is that they are conformally invariant. So this guy and this guy are invariant under conformal transformations. Okay.
Yes. First question is, if you generalize that 2-point function, say O1, X1, O2,
Yeah,
X2,
good.
would that be
Exactly.
delta 1 plus delta?
So the dimensions have to be the same, but if you were to generalize it by introducing the second operator at a different point, you'd have here the difference.
Can there be operators with a different?
They cannot.
deltas?
It's 0. No. If the operators with different deltas, so if you have, for example, O1, O2, where delta 1 is not equal to delta 2, things 0.
And the second question is, this U and V, are they similar to Mandelstam variables we see in UFT, or is there a reason?
In what sense? So they're conformally invariant. So you know, for example, that if you apply conformal transform, you see, if I encode my endpoint functions in terms of U and V, at least I know that expressions that depend on them do not change at the bottom. I'm introducing it now, especially after I talk about 3-point functions, because they were going to be important when I move to 4-point functions, which is the main star of the bootstrap. So now that we introduced these two conformally invariant combinations of these space-time positions, let's go to 4-point functions. Okay, now I will move on to scalars. Phi x1, phi x2, phi x0, phi x4. And this thing depends now non-trivially. This guy was a constant, not depending on space-time. But the 4-point function now is the first time where you do start having some non-trivial space-time dependence that does not depend on the I lost my train of thought, which is a function of the space-time points. X1, 2, and here, because now I'm dealing for identical scalars, the powers is delta phi times 2 and x 4. Okay, so this is what conformal symmetry constrains the 4-point function to be. There's some kinematical dependence in terms of this denominator, And then there is a function of these conformal cross ratios, U and V, that you have to determine. And so our goal is to try and see if we can, determine or constrain this function G. Yeah.
Is there any reason why we only consider identical?
Yes, to make our life easier for the purposes of this presentation. But you can do more complicated things. Once again, you see, if here I start having things which are not scalars, I have to start having indices, right? Like, say you've got a vector, you have like an index mu, etc. Then I have to compensate for that index structure with some invariant on the right-hand side. So I'm going to have expressions which are much more complicated. So if you see any text on CFDs and the bootstrap, they start only talking about scalars and they say, oh, you can do things for other operators, which are called spinning operators, anything which is not a scalar is called a spinning operator. I should have said at the very beginning, and I forgot, that in the notes of, so this obviously is a kind of a very quick run through some of these ideas. There are some wonderful texts, pedagogical lecture notes that I've given the links to. There's a set of Tazi lecture notes by Davidson and Staffen. There's some Wiseman lecture notes by Chichester. And there's a very comprehensive review on the bootstrap by David Poland, Slava Richkov, I forget the other authors. But if you looked at the notes, you can find, reviews with all the dots, all the T's crossed and all the I's dotted there. Okay, so we are at the point where we have a 4-point function, conformal symmetry equals this structure. This is an unknown function of U and V that I would like to try and determine. Okay, so let's park this for a minute. How can we determine this? Or how can we obtain, let's say, some kind of condition, some consistent condition that can give us a constraint on these functions? There is a very important object in conformal field theory, which is known as the operator product expansion. So let's pause here. In order to do more with this, I want to introduce now a new concept, which is called the operator product expansion. This is known as an acronym as the OPE. What is this operator product expansion? It is what happens when you take two operators and you bring them very close together. In that case, you can think of it almost like as a kind of scalar expansion of operators. You bring two operators together, and then you can express this product in terms of an infinite series of single operators at that point. So let me show you what this thing looks like. I have, let's say, 5x, 5y. In the limit where x goes very close to y or vice versa, I can re-express this as the sum over all the operators in my theory, a priori, of some constant, which I call, right, phi O, phi for this operator, that operator, and O for the operator that's being sum, or sometimes we say exchange to kind of make it visually look a little bit like what happens in scattering. There's a reason why I call this thing f, and these 3-point function coefficients are also f. So up to some normalization, they are the same thing, interestingly enough. And then you have also a differential operator, which depends on the difference of x minus y, some derivatives acting on y, and then hits the O's with the important caveat that this is a sum over all primaries of my theory. So I remind you earlier on, we define primaries as operators annihilated by my special conformal transformations. Some, you can think of them as lowest weights in this conformal representation. You can produce all the descendants, all the other operators in this infinite dimensional representation by acting with derivatives, but it helps me organize things like the operator product expansion nicely. If I know the primaries of my theory, I can write the OP in this nice way where all the descendants are captured by the explicit form of this differential operator. Okay. So sum over all primaries. This thing here is known as the OP coefficient. And up to normalization is the same as the 3-point function coefficient. Very good. Now, why do we care about this? Well, we care about this because you see what happens if I take this operator product expansion and I use it, e.g. here, I can rewrite this 4-point function of these scalar operators as the sum, the infinite sum of the sum over all primaries of a 3-point function, right? Because I can rewrite this phi x1, x2 in terms of that guy, which is summing over primaries. But then I have a 3-point function to compute. And 3-point functions, I know, because the 3-point functions, well, at least I don't have to do something complicated because they're determined. If I know my 3-point function coefficients, I have everything that I want to do about this correlator. And in the same way, I can reduce any higher point function to smaller and smaller endpoint functions, down to 2- and 3-point functions, which depend only on the normalization and my structure constants. So this is a very powerful tool because it allows you, so the OPE allows compute any endpoint function in terms of 2- and 3-point functions. Any questions about this?
Doesn't really have a great question right now, but like, in terms of this theorem, how is that going to check? So is this like, some theory can always reduce that? Theorems that allows you to obviously reduce.
And these theories are not free. So it's not like, you're kind of, looking in some limit where the theory becomes free, etc. So this is just a property of conformal field theories. Don't think of it as a non-perturbative QFT, right? You can have arbitrary coupling and you can always do that. In fact, this is it's a non-perturbative discussion. So you're just using this property of operators. You can take a big one. You see, I'm kind of cheating here. It's not as simple as I'm saying it because you're reducing this 2-point function, but you're introducing an infinite sum, a sum over all the operators. So if I want to solve my theory, what do I need to do? I need to know all these guys and all these guys, all the operators and all the 3-point function coefficients. And for that reason, that information is known as the CFT data theory. Yeah.
Mixed theorem is contained in there, where only one of these coefficient is non-zero, which is when just the identity. You can think of mixed theorem.
So the identity operator is always part of the spectrum. That's right.
The only non-zero there is when the prime is actually going.
The only non-zero field here.
Sorry,
or if you wanted to think of it.
The coefficient in a free theory.
Yeah, good. Yes.
Would be with the identity there. That would give you mixed theorem. So with free theorem is contained.
Sure. For free fields. Yeah. Sure. I'm going to discuss generalized free fields later on, for which that's no longer the case, but.
So you're summing over all the operators. How do you determine which operators to sum over? I mean,
very good. So in principle, you sum over everything, and whether this thing is contained or not is determined by whether this 3-point function coefficient is 0 or non-zero. So that's information about my theory. So in principle, if you know the spectrum and you know the operators, which one is appearing in the OP depends on the value of this OP coefficient.
I just want to check what you said, can they close together, but isn't it in a conformal field theory?
So I mean, you can
only holding normal PFTs when
I mean, you can do a conformal transformation if you want, but I mean, you can still define sort of the difference. So you can, this thing has a radius of convergence. This thing depends on the, how the distance between these two things. That has a meaning.
Is it obvious a priori that the series is convergent?
It is not obvious a priori. So you define it. It is convergent up to the next insertion. So for example, if you've got a 4-point function, this thing is convergent until, so, the choice of which OPE you can take corresponds to the choice of quantization scheme. You can perform radial quantization, let's say, around this insertion point. And if this guy is encountered before that guy, you can, that's where the series converges. And as we'll see in a minute, when you start doing OPEs between different pairs, that corresponds to different quantizations of your theory. Good. So what do we do with this? I'm going to do exactly what I said. I'm going to take this 4-point function. Let me see how I'm doing. Excellent. And I'm going to apply the OP and see what I get. Very good. So let's take this 4-point function. x1, x2, x3, so on. And let's apply, in this particular case, the operator product expansion when I think of these two guys close together, or when I kind of expand the OP, when I do quantization around point x1, for example, and x3, x4. Apply this formula and see what we get. So what I'm going to get is a double sum over, let's say, O and O prime. There's one sum coming from the OP of these two guys, another sum coming from the OP of these two guys. A priori, these are over different sets of operators. There's also going to be two sets of OP coefficients, phi, phi, O, phi, phi, O prime. And then I'm considering this inside a correlation function. And here, just write times, write it underneath. I have the following, I have two sets of these differential operators, C, X, 4, 4, 4. So what this thing tells me is how, these are not just primaries, right? It's a collection of primaries and descendants. But the thing that I can do from this expression is to remember that the 2-point functions are only non-zero if the operators that appear have the same conformal dimension. And I can use this. So this is like a delta function, like a Dirac and Kronecker delta in the space of conformal dimensions, and it eats one of my sums. So I can rewrite this as a sum over a single set of primaries. When O is the same as O prime, which is the only case in which I get a non-zero answer for this 2-point function, I end up obtaining the square of these OP coefficients because O is the same as O prime. And then the rest I'm going to call some function W, depending on the operator dimensions and spins of xi. Okay, so I've reduced this 4-point function, which should have this form, and I'm trying to determine this GUV, into an infinite sum of this kind of structure, 3-point function coefficients squared, OP coefficients times some function of xi. Now, it turns out that if I compare this expression with this expression, so let me call this one, this guy 2. So comparing 1 with 2 gives me an expression I can solve for G of U of V. So GUV is the sum over all primary operators phi, phi, O times something which depends only on U and V. Okay, this is non-trivial. I'm not showing you the details, but if you see what these things look like, write them down, and so forth. For G, you get this. Now, have I just replaced one symbol with another symbol? Well, kind of, but it's important that I use this particular here. So this is a very special object, and it's known as a conformal block. Now, why conformal blocks important? So conformal blocks are important because they're completely determined in terms of the kinematics of your theory. So in fact, if you know them for any theory in a given dimension, they're the same for any other theory, don't depend on the dynamics. In fact, conformal blocks, if you want to kind of go a little bit deeper, how you determine them, they're eigenfunctions of some operator known as the Casimir operator, so you can solve for them. They are known, so the G's are known in closed analytic form in even dimensions. And they're known as approximations in all dimensions. So you can sort of approximate them using method by Zamolodchikov also in even dimensions, but they're known in closed analytic form in D. And in the notes, if you are curious to see what these things look like, they are some products of hypergeometric 2f1 functions. And in 4 and 6 dimensions, they become sort of bigger and bigger products of these hypergeometric 2f1 functions. Okay, very good. So this is cool. Now, how can I use this information to arrive at what I want to discuss, which is the Bootstrap program? So the Bootstrap program does the following thing. Any questions up to this point? More or less okay? Yeah. Yes. So you might come back to me and say, hey, why did you choose to do the OP between this and this operator, and that operator, and not, for example, this, and those are the two? Excellent question. You can. And in fact, we can pictorially draw what this would look like to motivate some language. So let's say that I have phi 1, phi 2, phi 3, phi 4. And let's say that when we perform the OP, we use kind of scattering amplitude notation to show that these two guys exchange an operator O and give me, you see, because of the way that I wrote things over here, you have these two guys taking the OP of phi 3, phi 4, by which I mean phi valued at position x2 and so on, and they exchange an operator O. Now, why do I use this pictorial notation? Because this looks a little bit in scattering theory of the nest channel process. But I could do something else. I could do phi 2, phi 1, phi 3, phi 4, and I could do this. Which looks a bit like a T-channel process. And in this particular case, because it doesn't matter how I choose to perform the OP, the value for the 4-point function should be the same. These two processes should give the same answer. And as we'll discuss in a second, that leads to a set of constraints that are non-trivially obeyed by the safety data. Now, if you really want to sort of be careful, there's also another way of doing these contractions. Instead of doing 1, 2, and 3, 4, and also 1, 4, and 2, 3, you can also do 1, 3, 2, 4. And that's a U channel. There's another channel. It turns out that for scalars, there is no additional information in the U channel if you already know what's happening for the S and the T channel. Okay?
This is the same as crossing symmetry.
Precisely. So this is what we call crossing symmetry by the use of language. Crossing symmetry for these 4-point functions. Excellent. Okay. So now let's see what this crossing symmetry implies for these functions GUV, because I've advertised that they're going to lead to a set of constraints. The way that I have computed this quantity was by doing this pair of OPs. If I am lazy and I want to see what this looks like if I were to compute it in this way of doing the OPs, it's sufficient to notice that the only thing that changes is that I can replace x1 with x3. You can convince yourselves that the expressions that I get will just get this index relabeling, or in terms of my cross ratios, u goes to v. If I do this, I can get an expansion of my 4-point function, the T channel now. Like so. So I get, let's write it up here, 1 over x1 to phi, x before, once again, to the 2 to the phi, u over v delta phi, then the sum of operators phi phi o squared g delta j. Okay, so this is again a non-trivial calculation, you just perform this change, you shift, rearrange things a little bit. By doing some changes of variables, you can recast the t-channel evaluation of these 4-point functions in terms of the quantities that are using the s-channel version of this evaluation of this 4-point function. And now this is very good because if I equate the two, equating S and T channels, gives me the so-called crossing equation, an equation that enforces crossing symmetry. And my crossing equation, if I cancel out common factors, is I phi O squared G delta J V equals U V delta phi, sine over the same spectrum of operators, because here I have the same external operators, phi, 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 phi. F squared phi, phi O G J. Okay, so this is what happens if I equate the left, the S channel, and the T channel way of evaluating the 4-point function. This is my crossing equation. And it turns out that this crossing equation is not automatically satisfied by my CFT data. So what does this thing depend on? It depends on my 3-point function or OP coefficients, the spectrum of my theory, dimensions delta and J, and that's it. And it is not something that is trivially satisfied. It depends continuously on these two real parameters, U and V. And it imposes the crossing equation, and we're going to write it here. Crossing equation. Imposes non-trivial constraints on safety data. Any questions?
On both sides, that should not be GUV, right?
Say again?
On the sides, that should not be GUV.
It is GUV. So I've done, I mean, originally it's not, but then I can perform some transformations. I can rewrite things so they look GUV. So in fact, I can bring this. I think you might be right, and it should be GVU. Thank you. Up to this. Thank you. Good. So I can bring this thing to the left-hand side. So let's massage this crossing equation a little bit. Because I have the same, all the operators that I have in my 4-point function are the same. The OP coefficients are also the same. So I can bring this guy to the left-hand side, and I can define, so with some new function, f delta j, which is this difference of these conformal blocks. Rewrite my crossing equation as a sum operators of f phi phi o squared f delta j as a function b equals 0. Loop. So this is an important quantity, which I will use as the starting point for my technical talk tomorrow. You can think of this as a sum rule. It is a sum over the spectrum of primaries of your theory that has to be 0, so it provides a set of constraints for your CFT data. Great. So let's say that I would like to now use this. I told you that it provides non-trivial constraints. Let's solve it. Yeah. Let's just go ahead and see how I can solve this. Well, that's very hard for various reasons. The first reason is that this function depends continuously on these parameters UNV. So you've got functions that have to be satisfied everywhere on this two-dimensional real plane. Second problem is that usually the sum here is non-compact. There's an infinite number of operators that contribute of primaries. Third problem is that the dependence of these conformal blocks on the delta and J as well, on the dimensions delta is nonlinear. Linear dependence delta. And if you were to try and, let's say, do some kind of optimization to try and solve for the values of deltas and f's. So you see, determining the f's is easy because they're just multiplying things up front as a coefficient. It's kind of a linear thing that you're trying to determine. But determining the deltas, which are continuous, is very hard. You'd have a very non-convex, complicated optimization landscape. And non-convex optimization is hard. Yeah, so doubly infinite in unknowns, in equations, which depend continuously on UNV, plus nonlinear dependence on delta, which leads to a non-convex landscape for your data. So what you do? Well, you do something very smart. And this is what the 2008 paper by Ratazzi, Richkov, Tony, and Vicky did, where you say, you know what, instead of solving this problem, which is very hard, let me solve a different problem. And the different problem is the following. Consider solving instead the following. Act with a linear functional alpha on these functions f of u and v. So I hit this, get the sum of operators, phi o squared, bless you, of alpha f delta j of u equals 0. Okay, so if this is satisfied, if I act with the linear functional alpha on this thing, it still has to be satisfied. Okay. Now, I can choose here the following two conditions, or make the following two assumptions. The first one is that alpha, when f is the identity block, so the identity operator has dimension 0 and spin 0, it's just the identity operator. So identity is 1, I can choose that as a normalization condition. And the second one is that I would like alphas where anything else is either 0 or positive for all delta j. So you see, now I missed one very crucial element. So why do I want to do this? I would like to arrive at a contradiction that invalidates certain assumptions that I'm making. So a very important point is that if you're working with unitary theories, or unitarity, I should say, implies or guarantees that f phi o squared is positive. So unitarity means that this thing has to be a real correlation function. These f squares have to be, by consequence, some real numbers. And then if I normalize the identity, which always appeared in this exchange to be 1, and then if I find a linear functional, any real function for which all the other contributions that come after the identity are either positive or 0, there's no way for me to satisfy this equation. Because I get 1 plus positive plus positive plus positive plus 0, so there's no way of satisfying it. So if I find even one linear functional for which this is true, for a range of delta and j, then this cannot be satisfied, and I have excluded from my search the deltas and j's for which this false. This is a dual formulation of this bootstrap problem, and this is how these people introduced it. Instead of solving this direct equation of this primal version of the problem, to use computer language or computer science language, they solve the dual problem of finding these linear functionals. So this is a familiar thing in the language of optimization in computer science. And in fact, you can very efficiently scan using computer code that is very standard for the space of linear functionals that do this job. And that gives you a set of bounds over the operator dimensions that you can have, and also you can do similar searches for the OP coefficients. And in this way, and I'm wrapping up, you arrive at exclusion bounds.
How do you apply Hamilton infinitely many deltas?
So you scan over the functional space of deltas. You don't fix the delta. You scan over the space of. You see, you have a function, and then you can sort of solve and say when this thing is positive, when it's negative, and then you find some region for which this thing is positive, and then that region is excluded. So,
just one question.
Yeah.
What is a linear function? What is the
I'll tell you exactly how you write it. It can be, let me write it here. In practice, you can have A to be some sum, or some M and N. I'm Greek, I confuse my A's and my alphas. So alpha Mn, some, let's say, derivative of U. You know what? So as not to U, and we write in terms of some. This will appear in the following lecture. So I can introduce some new variables, real variables Z and Z bar, the complex conjugates. And in terms of that, we can define linear functionals. Evaluated at Z, for example, this Z bar was 1/2. So I can write some operators of this type. There's an infinite set of them with some coefficients. You can think of it as a collection of these objects. So I scan basically over the space of coefficients for this object. And then if I find even one, for which for a range of deltas, I cannot satisfy the equation, then I have an exclusion bound. So the thing that people do usually is they say, oh, let's look at the 3D Ising model. The 3D Ising model has a spin operator and has an energy operator. And I make some assumption, for example, for what my spin operator is. If my spin operator has some value here, I get some bound. You can look at the plots, but I get things that look like this. And you say that we should make it a bit sharper so that you see the transition here. And then you see that this is the value for which the 3D Ising model, funnily enough, sits. And you say, oh, if my spin operator takes this value, then my energy operator cannot be anywhere above this range, has to be below this range. So you see, here you have not specified the theory that you're solving for. You're looking in the space of CFDs, and you say, if I have an operator, scalar operator with dimension whatever it is, then I cannot have another scalar operator with dimension higher than some particular value. So this is kind of useful and cool. And at the beginning, people were excited because they saw like special theories kind of sat in certain features of these plots. But what gets even more powerful and cooler is that instead of just bootstrapping, and this is called the bootstrap equation, the bootstrap program, I'm finishing, you can consider multiple correlators at the same time. And then what happens is that instead of having, let's say, some exclusion plot along those lines, you get other exclusion regions, and then you isolate yourself in something known as an island. And this thing can be very, very, very small, sufficiently so that it determines the safety datum to very high precision. And what I'm going to close with is to say that this is a very powerful technique, this approach, which is known as the conformal bootstrap approach. You can determine the 3D Ising critical exponents record accuracy of about 7 decimal points. This is the poster child of this approach. And you can apply it to many, many different problems. You've seen there's hundreds of papers in the archive in this line of business. Crucially, it relies on in this approach, on the positivity of these OP function coefficients, because if these guys could be negative, then this argument that I am summing positive things doesn't fly anymore. There are extensions of this where you don't have everything being positive, but they can be organized together in terms of a semi-positive definite matrix. And there are packages that allow you to kind of run these things very efficiently. Okay, so these packages are known as linear functional packages or semi-definite programming packages and so on. So what I'm going to be discussing in the second lecture is the following. We've spoken about CFDs. Now we'll, in the next lecture at the end of the day, we'll talk about CFDs at finite temperature. And then we'll talk a little bit also about neural networks.
Great. Let's thank Kostis. So we had a number of questions during the talk, but if anybody has got an urgent question, go ahead now. Okay, then if not, I suggest, oh, sorry, Kostas.
So you phrased everything in the end in terms of the conformal block, right?
Yeah.
And so that's where the information about the dimension comes in, because these depend on the dimension, right? Do they also depend on the overall, like how many, whether you have fermions in your theory or not? Like if you say, well, you have bosons, are they different in that sense?
So
they don't depend on the dimension.
Yeah, so you can take into, I mean, so fermions, whatever, will have different dimensions, right? So we'll have like half integer.
Yeah.
So that's the only dependent.
No, I mean, the dimension of space-time. There's one thing. They depend on the dimension of space-time, but they depend, if you say, I want a theory that only has bosonic operators, or versus one that has also fermionic operators, would there be different conformal blocks?
No, you can arrange conformal blocks to something known as a super conformal block if you kind of package them together. So the conformal blocks are the same. You know, you can compute them for operators of different dimensions, whatever. You know, the bosons have some dimensions, and then you can combine them together into bigger structures known as super conformal blocks.
So if you want a supersymmetric theory, you have different conformal blocks in the end, then, or your constraints are going to be different than non-supersymmetric.
There is more that the constraint you can recap. Yeah, the constraints are stronger if you've got super conformal symmetry. As opposed to just being, you know, conformal symmetry. But you can always recast those constraints in terms of, you know, standard conformal blocks.
So, here's a question that when you focus on the on two conformal cross-sections.
Very good. It's not always very good. So you can use conformal symmetry to reduce irrespective of the dimensionality of the space-time. So maybe you're working D dimensions, I don't know, in 26. So you can use conformal transformations to reduce it always to two real variables. Great question. So the fact that I have U and V, and I can rewrite this in terms of the ZZ bars, does not have to do with the fact that I'm working in two dimensions. It's for any dimensional theory, but it depends only, the 4-point function at zero temperature depends only on two real parameters. Very good. And in one, you have only one, correct? Yeah. So in higher than two and higher, you use two. In one, there's only one. Great. Thank you for the questions.
Okay. Okay, guys, let's get coffee and we will get back here at 11.
So, quite used to.
Okay, guys, so welcome back. We will now have Thomas Lord's talk, which will be his technical talk, and he will be telling us about BPS stable gratuity and higher spin holography.
Okay, thank you very much, Robert. Okay, today what I'll talk about is large N vector model, which have a large N vector models in 3 space-time dimensions, which will have an ADS4 higher spin gravity dual. I'll be studying a supersymmetric model and do something similar to what I explained to you last Friday with Engelbrecht graviton states and some new heavy operators which are called Twitter states, and there the goal was trying to understand the role of these heavy operators to better understand black hole states and so on. Don't know what for sure the black holes would be in higher spin gravity in ADS4, but anyway, I'm going to do something similar to see what we get. So the talk will be roughly based on a collaboration that I made recently, a few months ago, with my student Jae-hyun Lee and young student Hyun-woo, and Dr. Xian Lee, who's now a postdoc in Louisville University. So still a big motivation or thought, I mean, the themes that we'd like to understand would be the thermodynamics of holographic ADS-CFT systems and the important roles played by black holes to understand this thermodynamics of ADS quantum gravity. For instance, the thermal phase transition called the Hawking phase transition, which is the thermal nucleation of large black holes in ADS, has been believed to be dual holographically to deconfinement transition in conformal gauge theories. Okay? They are shown to undergo certain phase order, first order phase transition at definite temperature. And this kind of phase transition is driven by a large number of heavy operators in the conformal field theory, which sees this finite N effect. And in the last talk, I tried to explain to you a BPS analog of these phenomena and these operators. There have been attempts to construct and characterize this large number of heavy operators in the BPS sector, let's say in the N=4 Yang-Mills theory. I've shown you some results and discussed something, but a comprehensive study of this program definitely faces a difficulty because it's very difficult to comprehensively study and solve the large N matrix QFTs. So the starting of this project to study the QFT with large vector valued matters was really technical when I started thinking about it around 1 year ago. If the large N matrices are so difficult to solve, let's do the similar problems with large N vectors and see if we can get more quantitative results and get a better lesson. Okay? Of course, so it was started as a toy model, but I didn't want to really work on really trivial toy model. I wanted to work on a toy model which has reasonable and interesting gravity dual, okay? Namely the higher spin gravity dual. With large N vector models, many of the studies become easier. Sometimes they exist really systematic methods depending on the observable you want to study. But of course, the physics become quite different from the string theories in ADS. So, for instance, compared to the Hawking phase transition, the deconfinement transition, which is first order in its nature, many of the partition functions of the large N vector valued quantum field theories turn out to exhibit a much milder third order phase transition. And that really has to do with the different nature of these heavy operators between the matrix valued QFTs and vector valued QFTs. Okay. And many physics is different, and it actually turns out that the vector matters, in a sense, shows a richer physics than the larger matrix gravities. So our original technical goal to solve things thoroughly and see get a better control of the system, that goal was only partly successful because the physics turned out to be, in a sense, much richer in a way that I try to explain to you today.
So,
yes, please. Please.
I thought the Gross-Wadia-Witten matrix model had a third order phase transition.
Yes, yes. So yeah, so this is exactly the same kind of phase transitions.
You're distinguishing between large N matrix and vector, but that's a matrix model.
Okay, okay, yes, yeah, yeah. Even for the so if you compute the partition function for either metric quantum field theory or the vector value quantum field theory, for both partition functions, there is a unitary matrix integral expression for both kinds of partition functions. The matrix appears universally. The matrix methods and vector methods in this auxiliary unitary matrix model shows up in a different, in the first case by showing potential given by two-body interactions from the matrix nature of the original theory. And here, like in the vector matter case, like the Gross-Witten-Wadia model, the potential is just external potential. So in both cases, matrix integral appears, and that's the Gross-Witten-Wadia matrix model that you're referring to. So even for the vector quantum field theories, partition function matrices appear. Okay. So what I'm doing today is study supersymmetric version of Vasiliev higher spin gravity in ADS4, which is known to be dual to certain supersymmetric vector model, supersymmetric Chern-Simons matter theory. I'll be studying some BPS sectors and do some similar studies as I explained to you in the Friday. For instance, study cohomologies. And last Friday, I didn't explain too much about the index, but I'll be studying also the larger index of this vector matter theory to study some aspects of the BPS phases. It will be much richer than the confined phase and deconfined phase of the matrix quantum field theory. And that rich structure I thought was quite interesting. So I try to explain the BPS phase structures by studying larger index and study the possible roles of these heavy cohomology operators there. In fact, there's no intrinsic need to rely on supersymmetry. In the case of n equal to 4 square mills, you eventually wanted to study a strong coupling regime to study the emergence of classical gravity. But doing the strong coupling calculation for field theory is so difficult. So there was some intrinsic technical need to rely on supersymmetry to do a lot of good calculation. Here is not the case because in the Vasilyev's higher spin gravity dual turns out to exist even for the vector models at zero coupling or recoupling. So you can do some recoupling quantum field theory calculation to see some interesting aspects of the gravity duals. So there's no really interesting intrinsic reason to rely on supersymmetric sectors. First of all, I'm doing so because that gives a good analogy to the similar questions in n equals to 4 Young mills. Secondly, even if there's no intrinsic need to restrict to supersymmetric sectors, if you do so, it's seeing a more modest sector. And it turns out that applying similar techniques to full sector and BPS sector, it turns out that you can do a much better calculation. So for some reason, I'll be sticking to supersymmetric sector, even though there's no real intrinsic need for doing that. Many of what I will present to you, especially the studies of the index using this unitary matrix model, many of the techniques that we use are applicable to the partition function as well at interacting theory. Of course, things become more difficult, but many things can be applied to non-supersymmetric observers as well. Anyway, with this, I'll try to proceed. So let me try to briefly overview the known models of the ADS for higher spin gravity and the three-dimensional vector model correspondence. The first model that has been presented more than 20 years ago was the ON vector model in 3 dimensions. Especially one of the models considered was a free ON vector model. And this model was suggested to be in some singlet sector, dual to higher spin gravity in ADS4, consisting of these higher spin fields with even spin. Okay? So phi is the quantum field theory vector field. And if you make an inner product of these vectors with suitable number of derivatives inserted, roughly corresponds to the bulk higher spin fields. And there are many ways of generalizing this minimal higher spin theory and the vector model correspondence by changing the symmetry group. You can change the DS into ADS into DS. As told you in the previous slide, I'll consider today an extension of minimal higher spin theory holography to a supersymmetric higher spin holography. In fact, what I'll consider is, in a sense, the maximally supersymmetric extension of the higher spin holography. And we often call this in the name of ABJ triality, because it's based on what is called the ABJ superconformal Chern-Simons theory, first studied by Aharoni, Bergman, and Jeffries. So the quantum field theory is three-dimensional n equal to 6 superconformal field theory, having 12 Poincare and 12 conformal supercharges. And it comes with this quiver gauge group, UN times UN prime. And these are Chern-Simons gauge fields at level K. And the matters that are charged under this UN and UN prime gauge group is bifundamental hypermultiplet and an anti-bifundamental hypermultiplet. Okay? So there are two complex scalars which are bifundamental this way, two complex scalars bifundamental in this way, and there are superpartners and so on. Depending on how you take the larger limits, n and prime or k, you get variety of ADS4 gravity duals. Okay? The most popular one, perhaps, is obtained when you take n and n prime to be same or similar and large, keeping k finite. There it has been known that you get a famous M-theory dual, an ADS4 times 7 sphere. This will be the setup that I will not discuss today. I'll be discussing alternative scalings, which leads to a string theory, and most importantly, a scaling which leads to a higher spin gravity dual. If you keep one of the ranks finite, like say n prime finite, say 1, and n to be large, and k to be large at the same time, with this ratio fixed as a tooth coupling, you roughly get a quantum field theory with n prime numbers of large n vectors. Okay? So in a sense, that this is a vector model with finite number of vectors. For instance, if you take n prime equal to 1, you get just vectors for each bifundamental fields, UN vectors. And the gravity dual of this system has been suggested to be a particular supersymmetric Vasiliev type higher spin gravity, has been explored by these authors. It has been argued to be have a gravity dual in which the bulk higher spin fields are charged under an U1 UN prime bulk gauge interaction with the tooth coupling given by this n prime over n. And it reduces to a free vector model of the type Polyakov and people studied when you take this tooth coupling to be 0. Okay? So you take the Chern-Simons coupling to 0, you decouple the Chern-Simons gauge field, you get the free vector models that was of the type originally studied by Klebanov and Polyakov. So this is a regime in which you have a gravity description of higher spin gravity. You can gradually think of cranking n prime up. Okay? You can crank n prime up to the order of n, and if you modulate k suitably, you get a completely different gravity dual description. If n and n prime are taken to be very similar, taken to be very large, and the tooth coupling kept to be very large and fixed, instead of higher spin gravity, you get a type 2B, type 2A superstring theory description on ADS4 times internal manifold for CP3. So by changing the second rank to be order 1, from order 1 to very large, you get a variety of gravity dual description. In one limit, higher spin gravity. In another limit, weakly coupled superstring theory. So the duality relation becomes more complicated, I mean, between CFT, higher spin gravity, and weakly coupled string theory. So some people call this ABJ triality. I'll be studying this kind of trial models, mostly in the higher spin limit, where n prime is mostly set to 1. Any other questions so far? This is the basic setup of the theory that I'll be considering. Yes, please.
But I think we don't call this derivation procedure from string theory, right?
Oh, derivation of Vasiliev. Oh, the Vasiliev theory, supersymmetric one, was constructed separately. Yeah. In the case of some simple higher spin theories, you use some collected fields in the vector model and try to derive the gravity theory. That kind of thing has not been done for this model as far as I'm aware of. Yeah. Just what's done is just constructing the Vasiliev theory independently, see that some structures mesh, and that's any other question? Great. Okay. So this again is a very technical slide. It's almost paraphrasing what I've explained about the cohomologies and BPS states for n equal 4 super mills. So if you survived last Friday's talk, never be scared of anything else, because all the logical structures will exactly be the same. It's just the difference between the field contents and the fraction of supersymmetry preserved. The logical structure is completely the same. So what I'm going to study first is, again, in this theory preserving 24 Poincare conformal supercharges, the minimally BPS states or minimally BPS local operators, meaning that among the Poincare supercharges, you pick one with definite spin and definite alpha content, and its Hermitian conjugate conformal supercharge, and demand your minimally BPS states or operators to be annihilated by them. Okay? And again, using the nilpotence of this Q, you formally regard this kind of local BPS operators as some kind of harmonic form. And if you want to study spectrum, shift to the description using these Q cohomology classes. So the structure is all the same. Again, I can only do the calculation easy in the weakly coupled regime. So I first consider free BPS operators and a subset of BPS operators which survive the interaction and continues to BPS at the leading non-trivial order. So in the case of n equal 4 Yang-Mills theory, we did it because it's the only thing we can easily do. Here you can give some more meanings, because even at very weak tooth coupling, zero coupling or weak tooth coupling, there are suggested Vasiliev theory dual. So you might regard this as something more realistic to describe this Vasiliev's high spin gravity. At lambda equal to 0, there's a suggested dual. At lambda equal to very small non-zero value, there's also a suggested dual. Okay? Although the gravity dual is a bit more exotic, it exists all the way down to weak coupling. And the only reason why I'm studying weak coupling is that, free BPS based construction, free operator construction is easier. If you consider some effect of interaction, I think that makes the structures a little bit more interesting, maybe more analogous to what happened in n equal to 4 Yang-Mills. And getting towards strong coupling, eventually you will be seeing string theory. So turning on a little bit of coupling, you maybe get lessons on whether things are moving towards the direction of string theory physics or not. So I think turning on a little bit of interaction would be interesting. Anyway, at strict lambda equal to 0, all gauge invariants of the invariant supersymmetry invariant elementary fields, you collect them and form arbitrary composite operators, they remain BPS. So there are two scalars which are bifundamental, the vectors in the fundamental representation, and there are two scalars in the anti-bifundamental representation. You can view them as column or row vectors, and there are some fermions. Okay? And you can dress these letters by holomorphic derivatives, which are supersymmetric derivatives, and form lots of gauge invariant BPS operators. Okay? It turns out that turning on interaction by studying the classical supercharged Q, many of these letters cease to be BPS. So many of the gauge invariant operators will get lifted to non-BPS by acquiring anomalous dimension. Taking a look at the scaling behavior of this coupling, it turns out that the lowest order anomalous dimension, it happens at 2 loop, unlike what happened in n equal 4 Yang-Mills, in which case the leading anomalous dimension is at 1 loop. Okay? So the study of the 2 loop BPS states is my main interest in this talk, which amounts to studying the cohomology classes of classical interacting Q. The problem is exactly in parallel mathematically. Any other question about this super technical slides? If you got the just understanding on rough structure, that will be enough. Okay? If you forget about the definition of details, you can just ask later if you're interested. So these cohomologies can be again divided into different classes depending on physical criteria. I'll be briefly reviewing what we have discussed last Friday in the context of n equal 4 Yang-Mills in a slightly related but in a slightly different flavor. Okay? What we first found in this construction of heavy cohomologies in the n equal to 4 Yang-Mills case was first we found a class which we call gravitons. Graviton cohomologies were those which constructed without referring to any definite signs of these n by n matrices. So these operators exist in an infinite sequence by changing the values of n. That's this way we called it monotonous operators in some way. So recalling this construction, it first proceeded by constructing all the single trace cohomologies, okay? From symmetrized scalars being the superconformal primary and their descendants. And they are physically describing one Kaluza-Klein graviton particle. And then you multiply these operators to find multi-graviton states and so on. Now let us consider all the remaining single trace operators, those which fail to be BPS at the single trace level. In the case of n=4 Yang-Mills, that's interpreted as all the other oscillating non-BPS strings. In this viewpoint, you can regard these graviton operators as the zero modes of a string, BPS zero modes of a string oscillation. All the other non-BPS single string states, the single trace operators, can be regarded as describing single oscillating, typical non-BPS strings. They acquire anomalous dimension, and by, let's say, using integrability technique and so on, if you go to strong coupling and so on, it has been known that the anomalous dimension scales like square root of the string tension in the gravity dual and so on. So even in the weak coupling regime, we just call this non-BPS excited strings on the worldsheet. The question is that if you put many of these single trace operators together to form multi-traces, and if these multi-traces include at least one or more these non-BPS single trace operators, it will typically remain non-BPS. The question that we have asked and discussed last week was, can some of them become BPS in some situation? So typically these multi-trace operators all acquire anomalous dimensions because each single trace operator is anomalous. If you put them together and let these oscillating strings and gravitons interact with each other, can they acquire binding energy back to BPS sector? Last week, we discussed this in terms of cohomologies and fortuitous cohomologies using trace relations. You know, Q acting on some multi-trace operators of this sort, they are non-zero in general if it includes non-BPS ingredients, but for particular value of n, it may vanish due to the trace relation of finite n matrices. In which case, we have a chance of getting fortuitous cohomology, which we interpret as the case as the oscillating strings interact with each other, form a negative binding energy back to the BPS sector. Okay? So these are one bulk way of trying to understand the fortuitous states. In the case of matrix quantum field theories, this kind of trace relation giving rise to more states was possible only when the operator is heavy enough, because operators have to be very heavy, the number of letters have to be large, scaling in n, for such operators to develop possible trace relations. So this kind of mechanism of having negative binding energy back to BPS sector was possible when the operator was very large in the larger limit. We're going to see what kind of things happen in the higher spin gravity dual, higher spin gravity using the large n vector models. To explain that, any questions so far, by the way? So to explain this in a bit detail, I'll have to explain a bit more about the trace relations, which I didn't really emphasize last week because we already heard of main trace relation in the previous talk on the first day. But for explaining more refined notion of trace relations in this vector model, I'll have to go back to the basics and give you a viewpoint of what trace relation could possibly mean for gauge invariant operators. For instance, again, go back to the case of n by n matrix theories. M1, M2, Mn, these are all n by n matrices, and I's are all row indices, J's are all column indices of these large n matrices, so n by n matrices. And think of the following way of forming gauge invariant. You're going to have n different letters to form gauge invariance. You're going to contract the rows and columns, but before doing that, you permute the columns in a suitable manner using the permutation of these small n different elements. If you permute the columns and contract with the rows at the same position, you're going to get lots of interesting multi-trace operators. If you don't do anything and just contract, you're going to get single traces of M1, M2, trace M1, trace M2, blah, blah, blah. If you make suitable permutations and contract, you're going to get a longer single trace operators and so on. Okay? So this is that gives you a various way of constructing multi-trace operators. Permute the columns and then contract. Okay? If you go through this procedure, you get an obvious constraint on finite size matrices, because if you make a linear combination of this certain number of permutation in a way that you anti-symmetrize more than n column matrices, they are column elements, they're identically zero. Because this column indices J's can carry at most n different values, and if you anti-symmetrize more than n of them, they're identically zero. This is the source of the trace relation. If your gauge invariant operators involves a structure which anti-symmetrizes more than column or row indices, it becoming identically zero is the trace relations of multi-trace operators. So is this point clear? So having this in mind, we can repeat the same logic to rectangular matrices, okay? Or even to any n prime equal to 1. And gauge invariant operators of these rectangular matrices also consist of contracting all the un indices and contracting all the un prime indices after this permutation thing. But depending on which one you anti-symmetrize, anti-symmetrizing more than n un indices will give identical zero of the same sort. Anti-symmetrizing more than n prime second indices will give zero for the similar relation, which I keep calling trace relation. Okay? Especially for the vector model, n prime equal to 0. You get very trivial relation of this sort if you anti-symmetrize two or more vector objects. You know, in the case J's are all 1 in n prime equals to 1. If you just anti-symmetrize the location of the two vectors, it just becomes 0. That's the trivial looking vector model trace relation, but this will be playing an important role for the construction of interesting operators. A very important such relation, very trivial looking, is the following. For instance, you have two identical bosonic vectors, n by n vectors, you just anti-symmetrize them. Then it's just 0, right? So this is the simplest kind of U1 trace relation that applies to the vector model. So if you act Q on certain complicated operator made of vectors, after acting Q on it, you find some vectors like this. This is identically 0 by U1 trace relation. So that leads to three distinct classes of cohomologies. One is, I just name it graviton because it'll turn out to be spin 2 particle and its multi-particle state. The first class are the monotone operators, in which you get single trace cohomologies and their products where you use no trace relation to construct out these cohomologies. The other two classes, I can say, is a fortuitous state, operators which become Q-closed thanks to certain trace relation. You can have U1 fortuitous states, you can have UN fortuitous states. The nature of UN fortuitous states will be somewhat similar to, in spirit, to the fortuitous states you find in the n equal 4 Yang-Mills theory. It appears only when the energy of scale dimension of the operator is very large, because this trace relation appears when you have more than n letters or so on. So morally speaking, they'll be playing the role of heavy black hole-like states, although we don't know what it means. For instance, these will be the operators which leads to the confinement transition of this system or so on. The role of NU1 fortuitous states will be a little bit novel thing in this kind of story, which I'll try to elaborate now. Any questions? Okay, so I've heard that I'm allowed to be a bit technical talk, but clearly I made it too technical, so sorry about it. It's suddenly becoming more technical. Yeah. Yeah. So let me try to explain to you what kind of BPS spectrum that we find with ABJ vector model at the free theory and when you turn on interaction. The single trace level, in the free limit, actually all the local operators in the free limit of this vector model can be arranging themselves into a multiplet of a higher spin current multiplet type. Okay, there's a conformal multiplet or superconformal multiplet containing currents with increasing number of spins. So they all arrange themselves the higher spin current tower. Even the BPS sector arrange themselves into some short multiplets, semi-short multiplet, and so on. In cohomology, the spin J multiplet starts from two scalars, column vectors and row vectors, contracted to form a single trace or single dot operator, and they are addressed by several numbers of derivatives, J number of derivatives to form a spin J multiplet. And then you form superconformal descendants and so on, as we did in the case of n equals 4 Yang-Mills. These are the free conserved higher spin current tower in the free limit. As soon as you turn on interaction, it has been well known that all the higher spin current towers should be anomalous. It comes from the fact that the conservation of the strict conservation of the higher spin current is possible only in the free theory. And no matter how weak it is, if you turn on the interaction, these higher spin currents will start to be only weakly conserved, meaning non-conserved. Okay? This non-conservation property makes these operators anomalous, acquire anomalous dimension, unprotected by the conservation law. So what happens is all the higher spin current towers, multiplets, except the multiplet containing the gravitons, will be anomalous. Okay? There will be, at the single trace level, there will be acquiring anomalous dimension at the two-loop level. The only thing that survives this interaction and remains to be the non-anomalous is the so-called stress energy tensor multiplet. Okay? It comes from the J equal to 0 multiplet from this primary point of view. So it's a contraction of these two scalars. This is the superconformal primary. If you consider this descendants of this primary operator, it contains stress energy tensor and give rise to the protected graviton multiplet. Okay? If you multiply this graviton, you can again get multi-graviton state, but all the other single trace operators become anomalous. Okay? And these can be the higher spin theory analog of the anomalous excited string states in ADS5 times S5. Now the remaining 4 Twitter states is trying to get extra BPS states by forming multitraces of both gravitons and the anomalous higher spin currents. As I told you, individual single trace operators, the higher spin current, acquire anomalous dimension, but by putting them together, they may exchange extra interaction to gain negative binding energy, proper binding energy, to come back to the BPS bound. Algebraically, we studied by the procedure of 4-3T. Find some multi-trace operators which become cube closed thanks to the trace relations of two types. Interesting thing is that one trace relation, UN prime translation, starts to enter in at the threshold energy UN prime. So when it's U1, such trace relation turn out to give more BPS multi-trace operators from order 1 low energy, even if n is extremely large. So they give rise to very interesting multi-particle higher spin particles bound, where each of the individual particle is anomalous, but combining them, they acquire binding energy to come back to BPS states. Okay? So there should be very interesting multi-particle dynamics, which bring them back down to the BPS sector. Similar kind of things can happen for using UN trace relation if the operator size scales in n. So this is the case very similar to what happened in n equal 4 square mil. But the vector model nature gives us a very interesting low energy multi-particle BPS bound states, which have, I think, little to do with the deconfinement or black hole, whatever it is, but it just gives rise to interesting multi-particle dynamics of the higher spin particles. So there are two kinds of Potiter states on top of the graviton states, which is monotone. So these are 3 kinds of cohomologies that you can construct. And we have constructed several of examples of this kind. Okay, any questions so far? Okay. So in the remaining time, what I'll try to do is the following. I'll change the gear a little bit, and I'll study the BPS phases in this BPS sector formed by these operators at various charges and chemical potentials and so on, to study what is called the BPS phases of this system. Okay? studying the larger n index and the BPS phases at large charges was an essential part of trying to understand the dual black hole entropies and so on, in the case of ADS5, CFT4 correspondence. The funny situation here is that we don't know what black hole is in ADS4 high-spin gravity from physical point of view. However, we have some minimal feelings of what can happen. If you go to very high temperature or very large charge sector, we expect the system will still deconfine. Even in the BPS sector, there's a meaningful notion of deconfinement. I think the entropy scaling like some powers of n. In the case of vector model, individual quark degrees of freedom has n degrees of freedom. So if the entropy or the free energy scales like n, we can call it in the system is in the deconfined phase. Okay? So if you can roughly regard the deconfined physics as the physics of the dual large black hole, that might be a thermodynamic way of characterizing black hole-like physics in this large and vector model-like dual. So including that, I'll be explaining to you many kinds of subtle and interesting physics that can happen in this large and phases. And I'll try to probe this large and BPS phases by studying the large and limit of an index, counting these operators. Because that's the remaining thing that I'm going to do in the remaining time. Please.
Are we only speaking in prime of one?
Yeah, in my study, it's always empty.
I thought that mechanism depends a lot on every end.
That's right.
That's must be simple. So
yeah. Yes. So for instance, if you're going to order, say this is 4 tweeters, you have to write down the similar operators of similar form in n prime 2 and show that it's non-Q closed anymore. So you can extend this operator into n prime equal to 2 operator in suitable ways, but now you have to contract the 2 n prime equal to 2 indices in some fashion. And that fails to be Q closed because there's no corresponding n prime equal to 2 trace relation, which makes this Q closed anymore. What's that? Yes. Yeah. Right. Eventually, it will be interesting to increase n prime to higher values and see what kind of changes happen. We are not powerful enough to do that yet. Some studies are being done recently by Alberto Zaffaroni's group, and they are trying to clarify what photoity can mean in n prime equal to n case, and so n prime and n being 2 case, and so on. But it's only at the early stage, I think.
Trace relation is not technically correct. Right?
That's right.
Maybe some other name.
Yeah. I'm always ashamed to say, yeah.
Maybe some anticipation relation, really.
Yeah, whenever I say trace is about matrices, right? The vectors, yeah. But there's often, I think an abuse of terminology, which is quite often allowed here, is that you take 2 vectors and make an inner product, and we often call this single trace operators. In this sense, it's a relation between these multi-trace operators defined by inner product. But clearly it's an abuse of terminology. I'm not sure what's a better word, but at the moment, so yeah, clearly I'm abusing. Yeah. Any other? So now I change the gear, realizing it's becoming even more technical. But again, I'll explain to you the salient structures of this partition function, and just remember that and follow me, please. So the larger spectrum entropy of these PPS operators can be studied from what's called the superconformal index. It's an index version of the partition function which counts these operators for the states due to operator state map. You take a trace over all these states or BPS states, you count the number of bosons and subtract the number of fermions. That gives a more robust structure, coupling independent, and so on. And you weight these states by suitable fugacities. And this exists of fugacity corresponding to temperature-like quantity in this BPS sector. Instead of giving weight of the states depending on its scale dimension or energy, to make it an index, you weight these states by the energy plus spin that the operator carries. So morally speaking, this is the kind of temperature-like parameter in the index, okay? Because it has energy. Other chemical potential can be included for the remaining part of the R symmetries. but optionally, you can turn it up to 1 if you like. The thing is that the index of this theory admits especially in the large K limit that I'm strictly interested in, weak tooth coupling limit, the index of this theory admits a simple unitary matrix integral expression. And that's the expression that Tarek has been mentioning at the beginning of the talk. So by various ways, you can get this matrix integral formula. So you have n by n unitary matrices, and this unitary matrix can be diagonalized, and its eigenvalues are phases given by e to the I alphas. So alphas are all the exponents of the eigenvalues of these unitary matrices. So if you suitably gauge fix this unitary matrix integral, you can get an integral formula for n eigenvalues for n by n unitary matrices. So I'll just take this matrix integral as given. I mean, defining it. If you don't understand this expression, you can just take it as a defining expression for the partition function index, which you'll use to get a large and approximate expression. I'm interested in getting a large and approximate expression for this index, or log z, which I call the free energy. And especially I want to do it by making a large and saddle point approximation of this integral. Okay? A large and saddle point approximation, which is a good approximation at large n, is taking this integrand, writing as an exponential of something, and that something is the effective action for this eigenvalue variables, okay? E to the minus s or something. And in the large n limit, you can get a semi-classical result for this partition index by finding a classical solution satisfied by all these eigenvalues, by extremizing the exponent, the effective action. Okay? By that, getting the classical solution, plug it into the integrand, we can get the expression for the large and free energy, and Legendre transform it to get the entropy as seen by the index. Okay? So this is what people usually do when one wishes to evaluate the partition function given by this large n matrix integrals. Okay? And you have to do this kind of business, you have to know the structure of this effective action. The effective action consists of two terms. Okay? If you exponentiate this first term, it's, I'm not sure if you can, hope you can see this structure well. This is called a Haar measure. It's unitary matrix version of the van der Monde measure. And this factor is obtained by gauge fixing an n by n matrix integral down to an eigenvalue integral. It's a Faddeev-Popov determinant-like factor. And necessarily, since you have killed all the off-diagonal matrix element to get this Faddeev-Popov measure, it's a product of roughly n squared different terms, okay? Depending on the difference of the pairs of eigenvalues. If you exponentiate it, the Haar measure contribution to the effective action will give you the two-body potential with recursive interaction. Okay? So it consists of n squared terms. Second contribution of the effective action is basically what stays in this exponent here. By the fact that it comes from integrating out in the vector valued matter, it gives rise to an external potential to each eigenvalue rather than many body interactions. Okay? So the effective action consists of two terms, two-body interaction and external potential. The usual large n matrix model setup gives us a lot of techniques and recipes for getting interesting solutions, large n solutions for the matrix models of these sorts. Okay? The thing to remember is that we are wishing to get very non-trivial free energy, saddle points of free energy, which sees the effect of n. For instance, to see the deconfined phase of something, the free energy should scale in the power of n. So in order to see saddles whose free energy sees this non-trivial effect of n, the Haar measure repulsion effect and the other effect should non-trivially balance to give us non-trivial solution for the saddle point equation. But if you barely look at the large n dependence, the Haar measure part of the potential consists of n squared terms, while the background effect external potential consists of n terms. With typical order 1 temperature, which is not scaling, n squared terms and n terms cannot non-trivially balance to give non-trivial saddle points. The force that you obtained from the two terms have different large n scalings. They never non-trivially balance. You see the non-trivially balanced saddle points showing interesting phase structures. It's often done that you scale the fugacity or temperature to be very large so that the second external potential part acquires an extra amplification factor. so that n times that amplification factor can balance with n squared. Okay? So that we are considering a large n limit in which the temperature is scaled to be high, inversely proportional to n, so that the first and second term can non-trivially balancing. Whenever I say large n limit here, I'll be always referring to large n and high temperature scaling limit. Okay? That's quite commonly done in this kind of matrix model analysis, including this Gross-Witten-Wadia type models. So the effective action, so for simplicity, I'll turn off all the other symmetry fugacities except for one temperature-like fugacity. And if you exponentiate this measure, the exponent is nothing but this. As emphasized, the first term Haar measure has n squared term, the second term external potential has n term. So you make the coefficient to be acquiring extra amplification factor by taking the fugacity to be close to high temperature. Okay. So the way of getting it is that you want this denominator coming from many derivatives to be 0 for this letter index factor to acquire amplification. And you have to basically take the temperature to be infinity, my modulus of x to be going to 1, or inverse temperature beta going to 0, up to suitable phases. Okay? Naively, you would have thought that x defined by e to the minus beta and beta going to 0, x going to 1 would do the job. But this is a funny index, funny object called index, getting -1 contribution from various places. So the numerator comes from bosons minus fermions. So if you take a naive x going to 1 limit as a high temperature limit, it doesn't give you any divergent factor. It's 0 over 0. That's because of the funny fact that we are studying an index with minus signs for certain fermion fields. The proper high temperature limit to take is to take x to be 1 up to a phase -1. Okay? If you take this x to be -1, for some values of this summation, the numerator doesn't vanish and only the denominator vanish. Yeah.
Sorry, that's compatible with the index with the Q.
This sign.
No, I'm saying if you choose X that way, is that compatible with Q still computing?
Oh, yeah. Oh, yeah. Q commutes with the integrals for any complex value of X, as long as the sum converges. Yeah. So fugacity taken to be complex is always okay. You know what is yeah. What is demanded by Q commuting with all these measures is that the charge is appearing in the exponent. They commute with Q. And X, Y1, Y2 being arbitrary complex number is fine. Is it okay? Okay, good. It's a weird fact that we are forced to use certain negative chemical potential. It will soon turn out to be complex chemical potential. But first, pause for a while to explain what this means. This technical fact is everywhere when you try to use the index for ADS5 times S5, counting black holes there, but I'm just going to explain what it means. So anyway, we balance the first and second term. We are forced to take x to be close to -1, and the beta, small beta, which is roughly interpreted as inverse temperature in the index, is giving rise to an amplification factor here because the denominator goes to 0 for certain terms. In this limit, the external potential can be simplified to be given in terms of suitable dialog functions. But to obtain this, an even funnier thing happens, because if you're going to plug in x equal to -1 when it's non-divergent, you encounter the fact that you have to plug in something for the square root of x. Okay? Square root, the exponent 1/2, basically stems from the fact that the scalars in 3 dimension have scale dimension 1/2. If you're going to take x to be -1, you have to make a choice of square root x converging to either +i or -i. You really see that you have to deal with a complex value of chemical potential to do this kind of analysis. And before doing anything, you have to understand what this complex chemical potential would physically mean and why we would have to do that physically. Okay. For instance, if you do any calculation with this complex fugacity, you have a potential given by a complex function, and the saddle points will be a complex deformed one. Okay, so alphas were already originally sitting on a real line, but it's with complex deformed parameter, the solution will be deformed into a complex plane. And the free energy and the Legendre transform entropy will all be complex. And you may think this is a nonsense. What does it mean to have a complex entropy as a function of real charge? It doesn't count any state. The meaning is that that's the necessary thing that you have to get the proper large charge approximation of the entropy from an index. So for instance, suppose that an index is expanded into gas T, where J is the charge. The coefficient will be an integer. It will be a degeneracy coming from an index after Bose-Fermi cancellation. At large charges, the degeneracy will be a large number, fast-growing number, but it may be positive or negative, depending on whether boson dominates or fermion dominates. If you blindly, so if you have done correct calculation to get a saddle point approximation for that, after saddle point approximation and the Legendre transformation, you're going to get a function which diverges quickly as J grows large, but oscillating between positive and negative numbers. Okay? And that is possible naturally only when you have a complex entropy-like function and a complex conjugate saddle and Legendre transform saddle, so that you sum over these two to get a real number. If you sum over the two fast-growing complex functions, complex conjugate to each other, you'll be getting an envelope function which grows very fast, but as a relative phase of these two complex conjugate expression, you'll be getting an oscillating expression, cosine of the imaginary part of this effective action. So at large J, you'll be getting a fast oscillation between this envelope given by real part of this entropy function. Okay? So this realizes what happens in the typical index at macroscopic charges. Okay? So the physics of this complex chemical potential is that it demands you to get an equally contributing, mutually complex conjugate saddle points to get a macroscopic degeneracy subject to this wild oscillation. So this is the physics of studying this complex fugassity. Any question? This is quite generic thing, and the generic this philosophy will be also assumed in this vector models analysis. So with this understood, now you apply the standard matrix model techniques. And what you have to do is in the complex alpha eigenvalue plane, which I call the theta plane, you have to determine the distribution of the eigenvalues, large n number of eigenvalues. Okay? They generally form a linear distribution on a curve, a complex curve this time, on a complex eigenvalue plane. And on this curve, you have to specify the distribution of eigenvalues to finally construct the large n saddle point solutions. Dealing with these complex saddles and complex curves is very difficult. An easy way that we figure out is that it's easier to find a bulk distribution function and from that determine the curve. Okay? So you get a locally holomorphic function of this complex eigenvalue theta on the complex eigenvalue theta plane, and the actual distribution of the cut of the eigenvalues is determined by demanding this complex function multiply d theta, tangential direction of the curve, to be real and positive, to parameterize the infinitesimal eigenvalue on that interval. Okay? So heavily using some matrix model techniques, we got this bulk eigenvalue distribution function from which you can compute lots of interesting thermal quantities. Okay? For the one-cut distribution, for instance. Okay? We could also get the free energy for the one-cut distribution, which is the following function of the rescaled temperature-like variable. We call that gamma is n times beta, which is held fixed in the large n limit. It's a rescaled temperatures function. Okay, if you get this one-cut saddle and plot the eigenvalue distribution curve, you can only do it numerically, unfortunately. Oh, sorry. At various values of chemical potential or charges, we plotted it numerically in this fashion. So different colored curves are eigenvalue distributions at different charges or different temperature. I'll get to it in a moment. I'll be discussing these free energies and the possible behaviors. You can discuss it as a function of this inverse temperature gamma. Also, you can Legendre transform this free energy and discuss things as a function of the charge, conjugate charge, which I call J. First of all, we discussed the large charge regime or high temperature regime in which gamma is small. Okay? There we expect to find certain deconfining saddles, because at very high temperature, n different quark components are expected to be liberated. Then you can do this all the calculation explicitly, including Django transformation and everything. And the grand canonical partition function, grand canonical free energy, is shown to be proportional to n divided by inverse temperature beta. So it has a prefactor n in the large charge limit, and this leads us to interpret this one-cut saddle as describing a deconfined phase, because it's the phase in which the contributions from n liberated quarks are visible in the free energy. Okay? And in this case, you can actually compute the eigenvalue distribution and eigenvalues distribution of the complex plane and the eigenvalue density. It turns out to be a very small segment near origin when high temperature is taken. And it turns out to be the following Wigner semicircle distribution on this small segment. So this is the Cardinal limit of this vector model's large and free energy. If you reduce K from very large one, eigenvalue distribution spread because there's more the repulsion factor from the Haar measure, it becomes more important. As the charge is reduced or temperature is reduced, the eigenvalue distribution turns out to make a very complicated curve. And if you can reduce J's and numerically get this curve until a threshold charge only, which is non-zero. So when J is reduced to a threshold value, which we numerically determined as follows, the eigenvalue cut hits a singularity of a background potential, which you obtain as follows in the scaling limit. And after hitting this background potential singularity, the charge is below the critical value, the saddle just disappears. One-cut saddle just disappears. Okay? One very clear thing we find is that the one-cut deconfined saddles exist only above a critical charge or a critical temperature. That's one thing we should remember. And since we are, okay, at high temperature, we find deconfined saddles. It sounds so natural. To complete the story on thermodynamics, we should understand what happens at lower temperature below this and what the phase transition is. So the next really painful thing was to determine the low temperature saddle. And this turns out to be really, really odd. I think it's the really funny aspect of the index of this vector model. If you consider low temperature branch of saddles, usually it's very easy, much easier to determine than the one-cut deconfined saddle point. For instance, in the Gross-Witten-Wadia model, they turn out to be a gapless saddle points. So eigenvalues are defining your periodic angle variable. They just eigenvalues just wrap a circle without any gap and I think topology of a circle. And the phase transition is a competition of a gapless distribution at low temperature and one-cut distribution at high temperature. Here, for some reason, which I'll only partly explain during my talk, the gapless distribution doesn't exist at low temperature. Instead, in our model, due to some interesting strange physics, the low temperature saddles at fixed gamma or fixed charge at low enough value turns out to be two-cut saddles rather than gapless. Okay? So again, by doing heavy calculation, especially my younger students, we got the eigenvalue distribution functions, and then from that numerically determine the shape of the two-cut eigenvalue distributions at various values of temperatures, and in this case, the filling fractions of eigenvalues between these two cuts. But it's a very technical thing, but at low temperature, just emphasize that we got an analytic expression for the distribution function for the two cuts and numerically determine the shape of this cut at various values of charges. Any questions so far? Okay, this seems to be becoming very technical. So I'll be showing to you the phase structures and discuss the role of this heavy operation and then finish. So some minutes left, right?
Sorry, how many minutes?
2 or 3 minutes left.
That's it.
Okay.
3 minutes, yep.
Okay. So what I'd like to discuss now in this last page is the possible phase transition. You know, if you consider vector models, using the fact that this vector matter theory is easier to solve, there's been a lot of work on the free energy of the partition function in the free theory and interactive theory. Supersymmetric or non-supersymmetric doesn't matter. Just use some large N techniques of this vector model to discuss some free partition function and interacting partition function to a certain extent. What they have shown is that at low temperature, there's always a gapless distribution. At high temperature, it's one cut gap distribution, one cut and one gap distribution, and they undergo the so-called third order phase transition of Gross-Witten-Wadia type. So at low temperature, what you have is you have a gapless distribution on a circle, but eigenvalue density on this circle, I should have drawn a picture, sorry. Eigenvalue density on a circle becomes very low at a particular point as temperature is increased. And if you take the temperature to be increasing to critical temperature, eigenvalue distribution falls to 0 at a certain point. Beyond that temperature, a gap opens up to a one-cut distribution, and the gap opening transition is of third order, and it's called the Gross-Witten-Wadia type phase transition. Okay? And these authors have even made a nicer observation or interpretation that this gap-creating mild phase transition is driven by those heavy operators, driven by the trace relations reducing the states made out of these heavy operators. Okay, so if you consider higher and higher temperatures, more heavier and heavier an operator will turn out to contribute. The phase transition point is the point where the trace relation reduces the number of these heavy operator states by trace relation. So this kind of trace relation is driven by trace relation playing only one of the two roles. Trace relation reduces the states, and this creates rather mild third order phase transition. In the case of vector model index in our ABJ theory, trace relation is playing two roles. It of course reduces the states as the operator becomes large, but it creates more states by fortuity phenomenon that I explained to you. This fortuity phenomenon means that if you increase the energy, more states turn out to be BPS by trace relation, and you get more BPS states, and that's making the phase transition more radical, okay? More singular than the third order phase transition. Okay? So what should happen here is that we have two-cut distribution at low energy. Beyond the critical temperature, one of these two cuts should disappear and form one cut. Okay? Certainly, it's a cut disappearing phase transition rather than gap creating one. And there's a general, I think, experience that such phase transition becomes more singular than this gap creating phase transition. Okay? I don't think it's a general proven rule, but in various models that turns out to be the case. Unfortunately, we failed to compute this free energy for the two-cut saddles. It's just too difficult to do some integration. We only constrain the phase transition temperature, and we only constrain the phase transition to be either first or second order, but no singular, no more regular than that. It's clearly showing that the phase transition is more singular than these cases in which the fortuity phenomenon is absent. Okay? And in a sense, the phase transition is getting more singular by including the interaction effects and so on. So I feel that it's getting more close to Hawking-Page phase transition, which is first order. Okay. So I think turning on interaction and studying the BPS sector make it looks a little bit close to traditional string theory phase transition. Anyway, I'm running out of time. I'll just say this thing. So the interpretation is that heavy operators made out of UN fortuity is responsible for this high temperature deconfined phase, because it's a phase with that this is N. The high spin bound states form that low energy coming from this U1 trace relation. These are the operators which dominate the lower temperature states. Okay? I didn't show you much formula, but by studying the behavior of free energy at two-cut saddle, you can get convinced that these U1 fortuitous higher spin particles bound are dominantly contributing to this low temperature phase. And the phase transition is the transition between these kind of states and these kind of states, I think. Okay? There are much more richer structures, only part of which we understand better, but I'll have to skip them. Since I ran out of time, I'll just probably finish by showing this concluding summary and some comments. Okay, so I'll finish here. Thank you very much.
Okay, any questions?
I'm not entirely sure what you meant on the previous slide of
Let me
so you're saying the index is for Jews, or at least so you're saying that additional states are becoming present as large values
Yeah.
That's what you mean.
Yeah. The thing is that, if you consider let's say the interacting partition function, being slightly anomalous or not, it's all included. So even if the operator becomes slightly non-BPS, it's all included. And the weight is very similar because I didn't explain, but the anomalous dimensions are very small for these higher spin. It's a non-planar contribution. So apart from this 2 coupling lambda, it has an extra 1/n suppression. So it's very weakly normalized things. So the interacting partition function shows almost the same behavior as a free partition function. But the index is very interesting thing, so that in a way that even if it's slightly non-BPS, it's just excluded, right? So in a sense, it sees the more drastic behavior. I think it's nicer because eventually one of our interests is further increase n prime to go to the regime in which this slightly renormalized operator becomes seriously renormalized, right? So in a sense, excluding this near BPS state from the start might be making the physics become similar to the strong string theory limit, in which this lightly renormalized one will eventually flow to a very heavily renormalized one. So that's the reason I think we see a slightly more singular phase transition getting more close to Hawking page. Yeah, that's what I mean. Excuse me.
Questions? Okay, let's thank Suk again for a
First lecture is next.
Because the contraction is also two-body. Our measure is a two-body pressure. Just taking large n, you get a non-trivial balance. And only it's a two coupling the cross involved.
Okay, so the last talk for lunch by Olivia, and she was telling us about configurational temperature diagnostic, the lattice gauge series.
Thank you. Good afternoon, everyone. I'm Vamika, and this is a topic, and this is the work is in collaboration with Dr. Nadeep Singh Dhinsa and Dr. Nosh Joseph. So this is the paper that I'm going to be talking about. So this is the presentation outline. First, I'm going to talk about the motivation and the problem statement as to why we need the theoretic thermometer. So in this talk, I'm going to talk about temperature estimator that we have introduced in this paper, in the previous paper that I have shown, which acts as an algorithmic test to check the algorithms and the calculations and any mistake that happens in the algorithms. And the entire talk is going to be about that, which we also call as a thermometer. So this is the motivation and the problem, then the theoretical background, and then the mathematical framework. Then I'm going to talk about the numerical implementation, some validation studies that we have done on the UN lattice gauge theory in the 1D, 2D, and 4D models. Then the algorithmic sensitivity, how is it sensitive to errors, some detecting some simulation errors, metastability, and sampling issues. Then some practical applications, and I'm also going to talk about the limitations and then some conclusions. Okay. So why do we need the field theoretic thermometer? So we have, like in molecular dynamics, we can, there is no like straightforward, for the canonical Monte Carlo simulations, there is no straightforward method to validate the algorithmic correctness. For example, which is available in the molecular dynamics in the form of energy and momentum. So the traditional validation issues are that usually the checks rely on the comparing the known thermodynamic observables, which are often not available in the novel systems. For example, if you want to study some new system, then how are you going to check whether your algorithm is correct or not? If there is something wrong happening with it or not. So then we need the diagnostic. We require the gauge invariant non-kinetic diagnostic that uses the sample field configurations to verify the thermal equilibrium. It is basically sample field. It's just based on the field configuration and how the field changes and how we detect the change in the entropy and other methods, which I'm going to explain in the next slides. So the core idea has been taken from adapted from the Rugg and Butler frameworks of lattice gauge theories using Euclidean action as effective potential. Yeah, so this is the problem statement. The goal is to rigorously verify that the generated ensemble truly samples the Boltzmann distribution with the target input coupling beta. So the estimator requires a suitable temperature estimator must be gauge invariant and local to the field, independent of the kinetic terms of fictitious dynamics, and low computational overhead for online monitoring. It works simultaneously with the observable that we are trying to calculate, and we do not need to first try to determine the observable and then try to determine the estimator and then compare it. We can do it simultaneously, which saves time. The deliverable is the microscopic estimator, beta estimator derived solely from the action SE, such that the ensemble average specifies that this is our input beta and we are going to derive the estimator beta, and then we are going to check whether the both are equal or not. So the verification loop would work like this. The target temperature would be the beta input value that we are putting in the algorithm. Then we are going to do some Monte Carlo simulation, Metropolis or HMC. Then there are field configurations that we are going to use, and we are going to evolve the field configurations using these HMC methods, and then geometric estimator, and then we are going to derive the geometric estimator and verify whether this estimator is equivalent to the beta input, that the target temperature that we have substituted in the beginning of the code. So this is the problem statement. This was the problem statement. And what is the theoretical framework idea? It has been taken from the Rugg's paper, which basically says that the inverse temperature is equivalent to this expectation value of some vector field, derivative of this vector field. And how to choose the vector field? The optimal vector field should be of this nature. And what this vector field is going to be is what I'm going to present in the next slides. So the field theory adaptation is that you replace the potential energy with the Euclidean action. And as the action itself is a gauge invariant, the estimator inherits this property itself. Okay. So getting into the mathematical framework, I'm going to give a bit background of it for the mathematics. We have a phase-space system. I'm sorry about the diagram. No physics is being harmed here. So we have a phase-space system. We have a microcanonical ensemble. For the microcanonical, the most important thing that relies here is the entropy. For this microcanonical ensemble is being defined by this equation, where this entropy in the later slides I will tell you about the thermodynamics of this entropy. But currently, it is more important is that its entropy, how it is related to the configurational states. So the choice of this microcanonical shell, the hypershell for this microcanonical ensemble, is based on this. It should satisfy this relation, and where the Hamiltonian should lie between these two energy shells. And then the entropy is being defined by this equation. Okay, so what happens? Let's just say that under an infinitesimal shift in the energy of the system from say E to E plus delta E, there is a shift in the there is a change in the disconfigurations, and there is a displacement in the configuration of the system itself, which is defined by this just schematic that has been given here. So with the small change in the configuration, this small change in configuration happen along with this vector field. Now, this vector field is the one that was being explained earlier, that was given as X in the previous slides in which the mathematical expression was being explained. So this is, now the choice of this n vector is this. That is, as explained earlier, it should be some del prime partial S in partial S E square. So This is chosen such that the change in the Hamiltonian is of the leading order of delta E, and which ensures that the increase in energy is uniform across the ensemble. So, making some necessary substituting this into the previous equation in the displacement, and the final transformed configuration space is being given by this equation, which is now gamma plus delta E, and then the n vector, where the del Q operators they have the usual meaning, which is being given defined in that equation. So, given now the change in energy has happened, uniform change in energy. Now, what would be the change in entropy? So, earlier the entropy for the previous ensemble state before the transformation was given by this equation, and after the transformation, it takes the form of that equation. And after doing some necessary Jacobian transformations, the change in the entropy is being given by this AB delta E and the ensemble average of this equation, which is del Qn, which is similar to what was being explained earlier by the Roots method. So now the thermodynamics, we know the inverse temperature is given by the partial derivative of S with respect to the partial derivative of entropy with respect to the energy. In the limit of delta E tending to 0, we have this equation, which can be now given by this particular form, which is now equivalent to the inverse temperature, and which is equivalent to the beta, which we are going to call as the thermometer, as beta estimator. So this is the entire derivation, the mathematical framework that I have walked through right now. How we derive the thermometer, how we derive the estimator, which we are going to use in our calculations and our numerical. So this is now divided into two parts. One part is called the gradient term, another part is going to be called as the Hessian term, and some different notations and values for this is being given here. But the important thing is the gradient, the Hessian, and the beta estimator. Okay. So the deriving the field theoretic thermometer from the action. Now we have the action, we have derived the gradient part, we have derived the Hessian term. Now we are going to substitute that in this particular expression, and we are going to get the beta and the thermometer for per configuration estimator. We are going to take the expectation value of that beta and convert and see whether it converges exactly to the input simulation beta. And this configuration, basically they have two properties, properly relies on the solely relies on the configuration action and is independent of the momentum. There's one thing I think I missed telling it before, that while making the substitution in this, I have made it, the change is only happening for the position, the displacement is only happening in the position coordinates, and there is no displacement in the momentum. The momentum is fixed. So as stated here, relies solely on the configuration action and independent of momentum. The term analysis dominant in high dimensions, scales with volume, and directional term subdominant, directional term, which is this one, is going to be the subdominant and is of the order of 1. Okay, so how are we going to go through this? We are going to compute the action, then from the action we are going to compute the gradient part, and from that we are going to compute the Hessian part and the necessary substitution, and we have the temperature estimator. After some efficient evaluation, some more points I want to throw here is like local stances. Operations are local, highly parallelizable on GPU and CPU grids. Sparse structure hastens a sparse diagonal plus near diagonal, no full matrix storage needed. Boundary conditions, periodic boundary conditions handled naturally in the sample calculation. So some simulation setup that has been done for this work, that is we have simulated in 1D for 48 lattice size. For 2D it is 32 cross 32, and for 4D we have 8 to the power 4 lattice size that we have calculated on. Some observables we have. This is beta m for configuration plus binning has been done. Then the sampling is the HMC method has been used, and the action that we have taken is the compact U1 action. So here are some preliminary results that have been observed that has been evaluated. The setup was for the 1D U1 action. The action is given by this term, and the Plackett angle is being defined here. Now, this allows for the exact analytical solution for thermodynamic observables, as we have calculated the specific heat and the energy, and we have seen that the results are with the analytical results that are available in the literature. Also, we have this third figure, by which we have compared beta input with beta m, and as we can see, the dots are like along with the beta, which says that like they are it is equivalent to beta, and it is with the 99.9% accuracy, showing the excellent agreement with the analytical beta. So this was for the 1D U1 lattice gauge theory, and similarly we did it for like 2D, and the agreement was again exact and the stability was high. So here we calculated the Plackett, the Wilson loop for different RNT, different areas. And again, we can see that beta is in agreement with beta m with the third diagram. Similarly, the same was being done for the 4D U1 lattice gauge theory. Here we were able to see the phase transition happening. This is like available in the literature that the phase transition happens around 1.01 beta, and which is like evident here. And the same is for beta equals to beta m. The same was it was in agreement. Again, the third diagram itself shows it. So, okay. Like, let's just say that we have done this thing, then we tried to calculate beta. Yes.
Quick question about a couple of slides before. So how do people usually define stability in the previous one? One more slide. Sorry. No. Just go forward. Slides. Yeah, you say stability was high. How do people usually define stability in this context?
How do we usually define
stability?
Stability. Oh, in the sense that like they are like in agreement with the analytical results. That is what we are trying to say here.
So what's the difference between you have some numerical agreement there, right, up to very good precision. Stability is something different, or is it just that fact?
Sorry.
Is stability the same thing, or is it that you have very good numerical precision, or is it something slightly different about, I don't know, the way that...
No, it's the same thing. Yeah, it means... Okay. So yeah, currently, like we were able to see whether it is working in agreement with the results. So what happens if we induce some, we try to induce some error in the code itself. So we try to change the distribution, try to change the sample distribution and see whether the result, whether it is showing us some error or not. And it was showing us that the correct one was like 1, and it could clearly show the sampling was now more towards 1.025. So we just slightly changed the sample distribution and the error was quite evident here. So which tells us that tells us about diagnostic power, that unlike simple observables which may settle to different value without obvious error flags, beta directly contradicts the input parameter. It was not nearby 1, and which was evident here. And automated checks with estimator allows for automated regression testing in code developments. Like whenever you're writing codes and you can like test it. Okay. So some practical applications: thermalization monitoring, tracks beta versus Monte Carlo time to determine whether the equilibrium is reached, more reliable than local observable. HMC integrator check, validate HMC integration steps and acceptance rates independent of Hamiltonian conservation. Code quality assurance, it tells you whether your code is use the standard regression test when modifying simulation codes. And extension potential, expanding the methodology to non-abelian theories and more complex lattices. you can move it to like non-abelian SU engaged theories, QCD finite temperatures studies, and topological freezing diagnostics. Okay, so here one more thing that can be that was not being said, and I would like to speak about it. Like mostly what happens is for larger lattices, you can ignore this part as this is the dominant part and this is the subdominant part. So in large volumes, the off-diagonal Hessian contributions and Dike terms become subdominant and can be neglected. So it also saves your computational time and most of the calculations that you have to go through. This slide mostly speaks about this itself. Okay. So I have already talked about the key advantages. I would like to talk about two limitations. The implementation requirements requires explicit calculations of derivatives, which can be complex for some actions. Like we are doing some hand calculations right now for the actions, which are like as the action increases, they become more complex. It might be very difficult to do, but then also we have some other tools to cope up with those things. So analysis consideration, it is not a phase order parameter. For example, here we tried for the placket observable and the beta M with MC time. As you can see, wherever there was some, this is for like the phase transition 4D human lattice gauge theory. What we saw here was that whenever there was like some change, there was some phase transition happening, there was some observable that gives us the result, we can see the spikes. But whereas beta M was clearly the same here entirely, and we can see some spikes here, which somehow tells us that it is not like you cannot use it as a contradictory to an observable. So it just acts as an estimator, and it's not some substitute for any observable calculation or anything. Okay, so key findings, already spoke about it, but introduces the field configuration based estimator derived from the Euclidean action, successfully verified across 1D, 2D, and 4D lattice models, demonstrated high sensitivity to algorithmic errors, and developed a simplified directional estimator for large volume. So there are some future directions. It can be extended to non-abelian SUN and QCD actions. The temperature the estimator can be leveraged to independently verify temperature and anisotropies, and integrating estimators into standard lattice QCD code base as runtime diagnostics offer a real-time feedback on sampling accuracy, and tracking temperature fluctuations near these sectors offer new insights into autocorrelation times as well. So these are certain remarks that we had. We are saying that that can happen. So some closing thoughts. Configuration temperature estimator offers a rigorous gauge invariant diagnostics. The estimator effectively tracks thermalization, while not an order parameter. It serves as an invaluable thermometer, and the method is generalizable and scales to higher dimensions. So you can move it to non-abelian and QCD. This much.
Questions for our speaker?
Can you apply this to a zero-dimensional theory?
Zero-dimensional theory, okay. Why not?
The matrix model.
Yeah, sure. I haven't done it, but yeah, why not? Like, we can try it.
What's the meaning of
So it's normal. Here, let me go to the action here. So this one. So S is equivalent to beta. This beta is what we are bringing it input. This is the temperature we are saying here.
It will be like a coupling.
Yes.
Okay, so then let's thank our speaker again. And now it's lunch.
What was done.
Yeah, I can hear myself.
Fair enough.
I'm a bit worried about this pen. It's,
There's not another black one there?
this is done. Yeah, that's good. And do we have an erase gun?
I'm scared.
For showing the slides and everything.
I'm ready when you are.
Okay, so let's start the afternoon session. First speaker will be Tarek Anos. He'll give 3 lectures and 2 lectures and 1 seminars on QFT on digital, right? So,
Correct, yeah. All right, hi everybody. So I'm gonna dovetail with what Lorenzo was teaching about QFT and ADS. I'm gonna talk about QFT in anti-ADS, anti-DS. And I figured that it would be a good idea to start with why we care about de Sitter. And I feel like somehow in our field, we talk a lot about why anti-de Sitter is important, but we really should be talking about why de Sitter is important. So I'm going to start by giving a history lesson. Today's a history lesson. There's not going to be a lot of high energy theory today. It's just going to be a motivation for why we should think about de Sitter. Okay? And the beginning is the observation that the universe at large distance scales is homogeneous and isotropic. Isotropic means that if you look in any direction, across the sky, it looks the same. There's no special direction, and it's homogeneous means that the state is symmetric. And so this is a very simple observation made thousands of years ago by early astronomers. They didn't even need telescopes to determine this. Just look at the sky at night. And it took a couple thousand years to determine that means that the most general metric that you could write down for such a space-time is looks like this. And I'm going to write down 3 options. One is going to sinh squared, chi squared, and the other is sine squared. And these correspond to 3 options. I'm going to write them down like this. One is negatively curved spatial slice. So spatial slices are either negatively flat, positively curved. And so this is the negative case, this is the flat case, this is the positive case. And they're associated with a particular number. And the particular number is, I can write it down for you as follows. If you want to work in the general radial coordinates, so I didn't use r, this chi should be thought of as like a radial coordinate, but the more standard spherical radial coordinate that you would write down is related to chi like this. So dr squared minus k r squared, d chi squared. And you can integrate this relationship to get r as a function of chi. And this case corresponds to k equals -1. This case is k equals 0. this case is k equals plus 1. And you can see k equals 0, dr squared equals d chi squared. So k equals 0, r and chi are the same.
Actually, it's just a typo. Last d chi square is sphere metric, right?
Correct. This one is the positive.
If you have already d chi square, it should be
Sorry, you're right. This should be d omega
omega, yeah.
2 squared. Thank you. Somebody's paying attention. And okay, so these are the spatial slices. So if a universe is flat, this clearly tells us that, you know, in all directions it looks the same. And then this quantity over here, which is going to be very important in today's lecture, is called the scale factor. The scale factor could be 1. If it's 1, then you get Minkowski space. So scale factor with k equals 1 is just the case of Minkowski space, which you've seen before. But more generally, if you have a homogeneous and isotropic universe, then this you can accommodate it with any metric such as this. And now we're going to try to understand how to figure out what A is. Okay? So how do we figure out what A is? Well, we need to do some observations. So I shouldn't have written so big. I'm going to copy this equation. Just give me a second. So now we need to do some observations. So what do we look at? What do we look at in the sky? What are nice bright sources in the sky? Any ideas? Stars. Stars and galaxies, formed of stars. And what do we look at when we look at stars? All right.
Brightness.
Brightness is a hard thing to measure because we don't necessarily know distances, and brightness goes down with distance. If you want a good measure of distance, you need some extra data. But one thing that is pretty easy to measure is spectra. So, for example, on Earth, we can take something like gas of hydrogen. So I'm just going to draw protons with an extra electron around them. And then we can try to excite the electrons out of the cloud of hydrogen. And there's going to be a typical spectrum associated with that, and they have to do with the atomic orbitals of hydrogen. And you're going to get some emission lines. It'll look something like that as a function of wavelength of light that you shine it. And so stars, mainly balls of hydrogen, we look at them in the sky and they have the same emission lines as on the Earth, right? Or we expect them to have the same emission lines as the Earth. Except for one thing. The stars are moving away from us. And the stars are moving away from us means that these emission lines get shifted. So maybe you have experienced this when you're sitting outside and somebody is driving very quickly, and all of a sudden the car passes you, and as it's moving away, you hear it go. It's the Doppler effect. So the exact same thing happens because the stars are moving away from us. These lines get shifted. And so one thing that we can do is we can try to measure these shifts. Okay? So how do we do that? All right, so let me introduce a way to analyze this metric. So a very simple way to do that is to consider something called conformal time and write it as eta.
define it this way. And with this definition, the metric, the drawing has served its purpose. The metric becomes the following. So the scale factor just pops out. And because the scale factor pops out of the metric, something very convenient happens in these coordinates. In these coordinates, light rays follow chi is equal to plus or minus eta plus some constant. That's how you know, well, you know that that's the case because say you're at some fixed point along the sphere, then this line would have d eta equals d chi, and that's a null line. Light has to follow such a thing. So let's draw our observation. So this is chi theta, and we're going to observe some star over here. And so we want to observe this the emission of some light from this star, right? So say we want to observe some emission at some frequency, some wavelength. Well, we need to resolve a cycle of the emission, right? So we need to observe some characteristic time for the light of a particular frequency. So I'm going to call that delta t. So lambda emission star is going to be delta t. And in these coordinates, that's equal to a. So this happens at some eta, which I'm going to call. So this line over here is going to be called eta emitted, and we're going to be the observer. Over here, sitting at eta observation. Okay. So this is so delta t is related to delta eta by this factor. And over here, we need to observe the same delta eta, which is not the same delta t, right? So in these coordinates, light travels at 45-degree angles. So we're going to observe the same delta eta, but we're not going to observe the same frequency, because the frequency observed will be delta t observed, will be a eta. The same delta eta en. These are supposed to be straight lines, and wasn't, so. Okay, and then we can see how much the light gets shifted by just taking two ratios of these numbers. These ratios of these numbers are nice dimensionless quantities, and so ratios of these numbers will tell us about the scale factor when it was observed versus the scale factor when we observed, when it was emitted versus the scale factor when we observed. So the difference between the spectral lines, the ratio. Okay. And now what we do is we Taylor expand this. This is equal to 1 plus eta a at time of observation times the difference
And so the deviation from 1 is what we measure. And we call this quantity the redshift, Z, which is known as the redshift. And the redshift is, so if you ever look at a cosmology paper, the redshift is actually the quantity, this is the unit that people use to discover histories of the universe. So you'll see this event happened at redshift 5, or this happened at redshift 10. And so now you understand why the history of the universe is measured in redshift. Okay? Now, notice one thing. If we were in flat space, the derivative of A divided by A would be 0. We wouldn't observe any redshift. So the fact that we observe a redshift at all tells us that we're not in flat space. And we do observe a redshift. So, we now conclude that the universe is not flat. So now that we've concluded that the universe is not flat, anybody who ever taught you quantum field theory in flat space, you should complain to them. Say, why are you teaching me about that stuff? It's not relevant. Universe is not flat. Okay, but we still haven't determined A. We just determined that it's not equal to 0, or not equal to 1. So how do we determine A? We need to do a few more experiments. Oh, I want to say one more thing before I go on to the experiment. This quantity right here, that quantity right there, let me erase this.
Can I just say the graph was a little off camera? It was on the opposite, so they didn't see. It's fine now. I'm just waiting for a good time to say it, but that's fine.
Okay, I apologize to the people online. You have to imagine a drawing based off the words that I said, for those of you online. I'm sure you can do it. It was just a drawing with two 45-degree lines. Okay, so this quantity right here, d eta A at time of observation divided by A at time of observation, this is called the Hubble constant. And everybody should be mad about that name because it's not a constant. This is the derivative of the scale factor divided by the scale factor at the time of observation. So it depends on when you make this observation. So this thing is not a constant, and it's criminal that it's been called the Hubble constant. So we should lobby the universe to not call this the scientific community. It's the Hubble number now. I can give you what this is. Do you guys want to know what this is? You don't. I'll tell you a number that will have zero relevance to your lives. I'll just say it out loud. It's I didn't even write it. Okay. So now we need to do an experiment to determine what AFT is. We know that AFT is not equal to 1. Now we need to do some experiments to measure AFT. And I need to tell you, I need to qualify a little bit more on what scales the universe looks like this. So the universe looks like this. I mean, clearly it doesn't look like this near the Earth. We know that the metric near the Earth is the Schwarzschild metric. Yeah. Metric near the Earth is the metric of around a spherically symmetric body. And we know that the metric of the solar system is not this either, because the solar system is very non-homogeneous and non-isotropic. So how far out do we have to zoom in order for this to be the metric of the universe? So any ideas? How big?
1 billion light years.
1 billion light years. Not that big. All right. Let me give you some sense of scale. Maybe we can guess together once I tell you the scale. So the size of the Milky Way galaxy is 0.015 megaparsecs. I'm sure none of you know what a megaparsec is. So that's roughly 50,000 light years. So you want to revise your number? Any guesses? Rough order of magnitude. You just say, you can give a number in megaparsecs. Just a guess, come on. Do you think it's 1 megaparsec?
What is the distance between Milky Way and Andromeda?
What is the distance between Milky Way and...
That's 4.2 light.
No, that's 4.2 light years would be the nearest star.
Okay, yeah, okay.
I would say it's a couple of megaparsecs. Any guesses? Any guess? Order of magnitude? 100 megaparsecs. That's the correct number. So the scale at which you have to zoom out in order to see the universe looking that homogeneous and isotropic is the scale of 100 megaparsecs, which you can see is tens of thousands of times the size of a typical galaxy, right? So we're talking about the scale of the universe where you can't even resolve galaxies anymore. Galaxies look like tiny little dots, like little ripples on an ocean. You have to think about zooming out that far in order to see the universe looking that homogeneous. Really, we're talking about the galaxies are microscopic scale at that point, okay? So really not something that we're used to thinking about. You're thinking about the biggest scales possible, right?
Roughly how many galaxies would be on this spherical range?
I think roughly on the order of tens of thousands.
This is like, would that also be clusters? Galaxy clusters.
I don't know what the technical definition of a galaxy cluster is. I don't wanna make something up just for the sake of the Instagram or whatever I'm being broadcasted on. Okay, so we're really thinking at very, very large scales, and at very, very large scales where the galaxies really we're gonna ignore the galaxies at this point. They're too small. They're like little ripples on the ocean. So we're gonna think of the whole universe as an ocean, and we've zoomed out. So what people do, because the scale is so big, is we think of the universe as a fluid. And everything in the universe, all the galaxies, all of the things inside the universe, treat it as a fluid. And we write down Einstein's equation. So all the students here are comfortable with Einstein's equations, cool. Okay, so we write down Einstein's equations. So Einstein's equations have the Einstein tensor is equal to the matter. And the matter is going to be we're going to treat it like a fluid. It's just a big homogeneous fluid. And the stress tensor for an isotropic perfect fluid in its rest frame, it looks like this. It's diagonal. There's a 0, 0 component, which we call rho. And then there's the three-dimensional IJ part, which is the pressure. So rho is the energy density. E is the pressure. And you can see that this is isotropic because X, Y, and Z are treated as the same. Okay, so then I can write down Einstein's equations. I'm going to write it in these coordinates. Einstein's equations are A dot over A squared is equal to 1/3 rho minus K over A squared. So K, remember, K is -1, K is 0, K is +1. This is the Hubble constant again. Then you have H dot plus H squared. is equal to A dot dot divided by A minus 1/6 rho plus 3p. So these are the Einstein's equations for this metric, and we have to add conservation, the stress tensor. And we get rho dot. B dot over A. B rho. So these are the equations that we need to solve. And these are kind of nonlinear equations. We have to make some assumptions about P and rho. So we'll make some assumptions now. So is it okay if I erase the stress tensor, but I leave the equations up? So these are the equations that we want to solve. Okay, now, so one thing, so we're going to assume something called an equation of state. There's something called an equation of state for the fluid. And the equation of state is where you assume that the density and the pressure are related by some number. So you take the pressure is equal to some number W. This is just a constant times the density. And conservation of the stress tensor can plug this relation in, and you'll see that the expression is dt log rho is equal to minus 3, 1 plus W dt log A. You can see that, right? dt of log A is equal to A dot over A. dt of log rho is rho dot over rho. So this equation makes sense. And now notice one thing, one very simple thing. If W equals minus 1, then you see that dt log rho is 0. And therefore, rho is equal to e to some constant times 2. I'm going to call this constant h. For particular reasons. Maybe I'll call it h tilde. Okay. But for w not equal to 1, not equal to minus 1, then we have the equation is very simple to solve. Yeah, the result is rho is equal to some constant times a to the minus 3 times 1 plus w. Both of them depend on time. So now the time dependence of rho and the time dependence of a are linked. Okay? And in order to figure out the time dependence, we need to plug into here. So I'm going to call this constant 3 H9. I'm going to call this guy H9. Sorry, keep changing. Can't decide. And if I plug this into here, then I have a bunch of options. So solving this guy, star, now gives a of t is equal to e to the 2, 3 times 1 plus w. That's w not equal to 1. And otherwise, e. Okay, so you see that if you have a source where the pressure is minus the energy density, then you have exponential growth of the universe, of the spatial slices. And otherwise, you get something polynomial. So it's the two cases, the two general cases, either exponential or polynomial. Okay, so so there's many different contributions to the A of t of the universe, and they come in either of these flavors. Okay, and at some point in the 90s, they determined the fraction that comes from w equals -1 and the other w's. So I'm going to tell you a little bit about that experiment. I'm not going to be able to give all the details. Here. So in 1998, and doing very well. In 1998, a survey of what are known as type 1a supernova concluded the following. So so it concluded that, first of all, K is 0. K is, the spatial slices are flat in the universe. And then it concluded that I'm going to call omega the fraction that contributes to A. So the fraction with w equals -1 was 0.72. So 72% of what contributes to the expansion of the universe comes from w equals -1. It's so the majority comes from stuff that makes it inflate exponentially. Let me just compare that to the amount of real matter, regular matter. So the baryons. There's something wrong with
that camera.
With the camera. So the amount from baryons, so that's W is equal to 1/3, is 0.04. Or 4%. So does that add up to 1? No. Does anybody know what the remaining contribution to expansion of the universe is? Huh?
Nobody knows.
Nobody knows. Do we know what we call it? That's right. So omega dark matter, which we do know it has a set W, which is W equals 0, is 23%. So another reason why you should be mad at your quantum field theory course. Quantum field theory course teaches you about the standard model, which really has no effect on the evolution of the universe. So you should be mad for two reasons. One is you're studying QFT in flat space, and the other is that you're studying a very inconsequential thing when it comes to the evolution of the universe. Okay, now this stuff, W equals -1, we call two things. It has two names. One is dark energy. I hate this name. Dark energy is a terrible name because who knows what it means? It sounds evil. It sounds awful. It was a name designed to sell headlines, I think. I prefer the following name, which is the cosmological constant. This one, other than the Hubble constant, this one's actually a constant. Cosmological constant. We also call this lambda. Lambda the cosmological constant. It's because it appears as a constant in Einstein's equation. I'll write it down later. So So this is experiment. This is not some.
They're not adding it to one.
Did I miss some contribution? Maybe I rounded. When
Please rounding.
Is there some curvature also?
yeah, maybe it's very small. I don't know. Okay, I'll have to look up my. I think probably what happened is that there's a decimal place that shifts it to one. I didn't write it down. We can look up the numbers if you want later. Okay, so these are experiments. These are experiments that tell us that the overarching evolution of our universe is driven by an exponential expansion. And as the universe evolves, the galaxies are going to spread apart faster and faster. So, something that we should understand. And let me mention, you guys have studied quantum field theory in flat space. As soon as you try to study it in this case with the cosmological constant being exponential, it becomes much harder. We'll see why in the next lecture. But this is the case that we want to study. Relevant for you. But that's not the only reason we want to study de Sitter. Let me tell you the second reason why we want to study de Sitter. Any questions about this so far?
We'll see it tomorrow, but QFT will become difficult at large scales. Or should I?
So you will always have to determine. So there is now a scale. It's the de Sitter scale, and whenever you say anything, you have to talk about whether the effect you're interested in it compares with that scale or not. If it's much smaller than that scale, then you might as well be in flat space. You're not studying de Sitter physics. So if we want to study de Sitter physics, you better be near that scale. Any other questions? That was reason one. The universe is expanding currently. It's expanding at a very, very exponential rate. The constant's very small. That's another problem. I'm not going to talk about that. But suffice it to say that we don't understand QFT in this background. Okay. So there's a second reason that we need to study, second motivation to study this. So let me tell you about a different time. So this last experiment that I described was in 1998. This is the observation of type 1 supernova as they move away from us. But actually, there was an experiment in, what year was it? It's sometime in the 1960s. So in the 1960s, a pair of antenna scientists named Penzias and Wilson they were working on an antenna in upstate New York, I believe, and they noticed that their antenna had some noise. And they had no idea what the source of this noise was. In fact, for a while, they thought that the noise was caused by bird droppings on their antenna, and they scrubbed really hard, and it never went away. And the only conclusion from all of their hard work was actually that the universe is filled with something called a cosmic microwave background. So streaming in from all directions is essentially very, very long wavelength light coming in from all sides of the sky, and it's everywhere. So you can get hit by these kind of long wavelength light rays all the time. And it turns out that this radiation is at a black body spectrum, around the 2.7 Kelvin. Very, very old light. Comes from the very early universe. And so here we are, the center of the universe. And we look out in all directions and we get these light rays streaming at us. And these light rays are coming from the farthest possible place that we can observe in the universe. Let me draw this picture in a different way. Here we are again. We look back at the past. I'm going to change pens. This is time. And we get these light rays coming at us. And the old way that we understood the universe, we thought that this light came very shortly after what was called the hot Big Bang. This time is called the hot Big Bang. And then people observed that the spectra, so you can look at the fluctuations around this light, and the fluctuations around this light was correlated. So the perturbations were scale invariant and correlated. Correlated across the sky. So light here and light here are correlated. But if you think of the hot Big Bang story, this light only could potentially be in causal contact with just this amount of light. And the light coming from here could be in causal contact with that amount of light, but there's no way for them to have ever come in causal contact, so they should have no reason to be correlated. So that threw out the hot Big Bang story. The hot Big Bang story was invalidated because the fact that this very old light across the sky was correlated. So what was the solution? Does anybody know the name of the solution at least? Inflation. So the only way that we have come up to explain the fact that all this light is correlated is inflation. Inflation, redraw this picture again. Here we are. CMB. The hot Big Bang. Forget about the hot Big Bang. The only way that we came up with is that actually there's a lot more cosmological history, and the hot Big Bang actually inflated from an earlier point, and this period had an exponential e to the ht as a metric that I had written before. So that is the earliest phase of the universe, known as inflation, and it explains both why the light across the sky is correlated, and it explains why the spatial slices of the universe are flat, why k equals 0. So there's a nice explanation within inflation for why k has to be 0. Even if you had positively curved or negatively curved initial slice here, once you inflate during inflation, that gets flattened out. We only see a part of the total spatial slice. So we can conclude two things from this. We've done now 2 experiments on our universe. And in both those cases, we noticed that our universe is anti-de Sitter. So maybe it's worth studying. So I have what, 13 minutes left?
More than that, more than 15 minutes more.
15 minutes, very good. Okay. So now I've given you a good reason to study de Sitter space. So now let's talk about what de Sitter space is. So okay, we're not going to talk about the real universe anymore. The real universe is really complicated. It's got all sorts of matter, light, dark matter. We don't know what dark matter is. But we do want to understand what happens when you study this exponential expansion and you put quantum fields on top. So that's going to be the realm of what we're going to discuss today and tomorrow. So we need a very simple scenario where we get this kind of exponential expansion. The simplest example, the simplest space-time with exponential expansion is de Sitter. So I'll tell you what I mean by simplest. So simplest means that we're talking about a maximally symmetric spacetime. So do you guys know what I mean when I say maximally symmetric spacetime, students? No? Okay. So what is a maximally symmetric spacetime? So the simplest example of a maximally symmetric spacetime is just flat space. So Minkowski space in d dimensions. Let's do a little test. So how many translation symmetries are there in d-dimensional Minkowski space? D translations. How many rotations?
DC2.
DC2.
Yeah.
Yep.
And dt minus 1 by 2.
Okay. Remember, this is minus dt squared plus dx1 squared So how many are there?
D minus 1.
So you have to select how many from these, how many rotation planes are there?
D minus 1.
No. So a rotation plane, you have to select 2 coordinates, right? Out of how many? How many are there between 1 and d minus 1? D? There's what? How many are there between 1 and d minus 1?
D minus 1.
Minus 1. D minus 1. Right? D minus 1 is 2. 1, 2, 2. Minus 1 is 3. 1, 2, 3. So they're picking 2 out of d minus 1. D minus 1. So d minus 1 times d minus 2 over 2 stations. And what are the remaining symmetries of Minkowski space? Boosts. How many boosts are there?
24.
You're not a student. Can the students tell me why there are d-1 boosts?
Fine.
Yeah. You want to pick one of these and one of these? d-1 boosts. So I'll save you the trouble of adding these up, but if I add these up, there's d times d plus 1 over 2 symmetries. So that's flat space. So the claim is that any maximally symmetric spacetime in d dimensions has d times d plus 1 over 2 symmetries. Same number as flat space. De Sitter is a spacetime that has this number of symmetries, but also has an exponential behavior to its growth. Okay, so how do we do that? How do we do that? Well, let me tell you the answer.
How about expansions and contractions? Like a scale symmetry. Is that possible?
Let me show you De Sitter space and maybe we'll discuss it later. Okay. Okay, two things I'm gonna tell you about the definition of De Sitter space. One is that it's a maximally symmetric spacetime. So that means it has d times d plus 1 over 2 symmetries. Two, it's the solution to Einstein's equations with no stress tensor. Remember, this is what we were calling the cosmological constant. So the cosmological constant defines a length scale. I'm going to call it big L squared. So this is related to lambda as follows. And so I've been using D, so we're going to work in D-dimensional spacetime. If you want to think about the space-time dimension of our university is 4, but we're just going to keep D general for today. And so we want to come up with a solution to this equation. We want it to have this many symmetries, and we want it to be in D dimensions. So now let me tell you a different geometry that has this many symmetries. Okay. What is a geometry that has this many symmetries? Well, let's think about the sphere in D dimensions. So how do I write down the equation for a sphere in D dimensions? So a sphere in D dimensions is the solution of an equation. So for example, a sphere in 3 dimensions, do you guys know what the equation for a sphere in 3 dimensions is?
Great.
Very good. X squared, I'm going to call that x1 squared plus x2 squared, 3 squared equal to L squared. Okay, how do we get, so that's a how many dimensional sphere? 2-dimensional sphere. This describes a 2-dimensional sphere. So if I want a D-dimensional sphere, how many more x's do I need to add? Up until what? X what here?
+1.
We want a D sphere. D plus. Okay, how many symmetries does this spacetime have? Let's or this sphere have? So what are the symmetries of a sphere? Rotations, right? You can rotate the sphere. How many different rotations does this, how many rotation planes does this sphere have? How many rotation planes does a 3 sphere have? Or a 2 sphere, sorry, a 2 sphere. The simplest one, the ball. It is. Right. How about this one? How many planes? So
6.
how many? So we did this exercise before, so you should just kind of remember it. What do we need to do to determine how many rotation planes there are? We need to pick 2 of these coordinates. Any 2 of these defines a plane that we can rotate around, right? So we have okay. So how many choices do we have for the first one? D plus 1. How many choices do we have for the second one? D. And we divide by 2. So see already the same number of isometries. So a sphere as a constrained equation in one higher dimension leads to the same number of isometries as d-dimensional Minkowski space, right? So a d-dimensional sphere has the same number of isometries as d-dimensional Minkowski space. So any guesses as to how we turn this into de Sitter? Swap one sign, very good. We're gonna take x d plus 1. We're gonna write it as ix0. And then we're gonna get x0 squared plus x1 squared. So now this is a constraint equation in d plus 1 dimensional Minkowski space. And this, by the exact same logic, has the same number of isometries. But now the isometries are no longer just rotations. So the isometries are now, we have E boosts and E this one, 2. No translations. So de Sitter differs from Minkowski space. It has the same number of isometries, but the difference is that now all the isometries are just boosts and rotations. There's no translations. No translations is actually one of the main issues with the fact that this spacetime is much more difficult than Minkowski space. In Minkowski space, we have the translations, and actually the translations are the quantities that we like as conserved quantities. So we write down our quantum field theory, we break it up into conserved momenta, 4 momenta, which has an energy. Energy comes from the time translation symmetry, spatial momentum comes from the spatial translation symmetry. But we don't have a time translation symmetry anymore, which means we don't have conservation of energy anymore. That's going to be a big problem when we discuss future. Okay, so this is how I write de Sitter as a constraint equation. Let's draw that. Okay, so let's draw the sphere, just as a reminder. We have, as I can't draw higher dimensional objects, this is going to be x1 and 3. And the sphere is isotropic in all the directions. And this L tells you that you can't go too far. Fill out this surface of size L. Okay, so what happens here? What does it look like? I'm going to draw it like this. X1, X2, this is going to be X0. And let's think about X0 equals 0 for now. X0 equals 0 is just a sphere again. Lower dimensions. I'm going to draw that like this. It's a circle. what happens as I increase x0? Actually, why don't I move this guy to the other side? So if I make x0 bigger, what happens? You have to go smaller? Does this look like a smaller radius? Larger. You have to get bigger. So it's going to get bigger. And keep getting bigger. So actually what happens is that this grows. And it also grows in the other way. If you go into the past, it grows as well. So when we think of de Sitter, we think about this whole space-time. Starts at t equals 0 and grows. But if I go backwards in time from t equals 0, it also grows. So when we think about the de Sitter of our universe, we don't think about the second half. First, just the growing part. So let's write down some coordinates on de Sitter. Okay, so actually, sorry. I'm going to do the exam. I want to be as clear as possible. So let's do the sphere again. So how do we write down coordinates on a sphere? So you guys know, so for example, if I want to write down the metric on the sphere, so let me show you a way to write down the metric on the sphere. Maybe some of you have seen it, maybe some of you haven't. So what you do is you start with the metric on flat space in d+1 dimensions. Let's do the two sphere, right? So let's start with the metric on flat space in 3 dimensions. Flat Euclidean space. This is the metric. And we want to solve this constraint, right? We want to solve this constraint in 3 dimensions. And I'm sure I won't surprise any of you if I say that one solution is to write x1 is L sine theta phi. X2 is L sine theta sine phi. And x3 is L cos theta. Right? If I plug this into this equation for d equals 2, then you'll get that this exactly solves this equation. And then if you want the metric on the 2 sphere, you just plug x1 here. You take the d of it, you square it. Take the d of it, you square it. And what you get is d theta squared plus sine squared theta d phi squared. So if you want to do it in d dimensions, for the d-dimensional sphere, it's very simple. What do? You start with xd plus 1. You say this one is L cos theta, just like that. And for all the lower xi's, you write it as L sine theta. And I'm going to call this omega I. This is the coordinate on a SD minus 2. Or, sorry, SD minus 1. So here you see this is the coordinates on a 2 sphere, and these are the coordinates on a circle. So the same way you write the coordinates on a lower dimensional sphere. And then what you get is that the metric is then d theta squared sine squared theta d omega d minus 1 squared. The only difference. Just foliate with lower dimensional spheres rather than just having a circle. Okay, now how do we get from that to the time-dependent space-time that is de Sitter? Well, remember, all we had to do was we had to analytically continue this guy to have an I in front of it. So we'll do that in the following way. We take theta goes to minus I tau plus pi over 2. And what that does is that turns this metric into ES squared. Oh, and sorry, this was divided by L squared. So we see that this sine turns into a hyperbolic cosine, and a hyperbolic cosine has an exponential in it. That's the thing that exponentially grows. And these are known as global coordinates on the sitter. So it's a time-dependent spacetime. There are no translation symmetries. There's just rotations and boosts. So translations of tau are not a symmetry of the spacetime, clearly. Because if you change tau, spacetime changes. Shift tau, it's not a translation symmetry. But you can clearly see all the rotation symmetries very clearly in this metric. The boosts are less obvious in this metric, but they're there. Okay, so that's one set of coordinates on this. These are called the global coordinates. The global coordinates are interesting because they cover the entire spacetime. But there's another interesting set of coordinates on de Sitter that is more relevant to us as observers. Okay, so let me, and the reason is that translations are clearly not a symmetry of the spacetime, but there is a way to write the space coordinates on the spacetime where it looks like there's a time translation. Okay, so let me show you how to do that. Oh, am I done?
Minus 10 minutes left.
Oh, I'm minus 10 minutes. I thought you were going to tell me when. I can stop now if you want.
I mean, up to you. Up to you.
Up to you guys. No, I can stop now. Well, let me give the. I'll take one more minute and I'll give the coordinates on the static patch. I'm sorry for. I didn't know I was over time. I'm sorry, guys. Okay, so there's another set of coordinates that we can write down. So instead, what we'll do is we'll take x0 is L squared minus R squared. Yeah, it's good that I'm showing you these coordinates. This is going to be from 1 to d minus 1. These are going to be the coordinates on a d minus 2 sphere rather than a d minus 1 sphere. And I'm going to take xd is so remember, the spacetime doesn't have a time translation symmetry, but if I plug this in, I do the this little exercise that I told you about, then the metric looks like this. Okay, so this metric looks like it has a time translation symmetry. I take t goes to t plus a constant, the metric doesn't change. So that clearly tells you that it's an isometry. This isometry is not a translation globally. In fact, you can tell because this metric has a horizon. You go to r equals L, the GTT component goes to 0, and that's just like a black hole. You might have seen that in a black hole spacetime. And this tells you that, so I'll say one more word before concluding. So the geodesic of t just somebody sitting at r equals 0, following t going up. So that's just a geodesic. So that describes somebody motionless sitting at one point. Okay, and if they look out, there will be a point beyond which they can't receive any signals anymore. That's at the distance r equals to L. What's happening is they live in a space-time that's growing very fast, and this space-time is sending signals that are going like this. And this person is looking back into the past, and at some point, the signals will have too much space-time to fly into, and will never reach our observer sitting over here. And that's what we'll experience in the future. If we look out far in the future, there will be stuff that exits from our observable universe. And that's what the experiment that we live in De Sitter is telling us, that things are leaving our observable universe. And I'll leave it at that.
Any one urgent question if you have? Otherwise, let's ask the question during the break. Thank you so much, and should we resume?
So I totally agree that because this is an single program, it's not, yes, so it can be anything.
I'm sure if he's gonna
You would expect it to be like knock down as you move away from the feet.
Based on what you're feeding in with the ball. Like, you know, that is. And
So what we're thinking of, because I mean, Ellie doesn't like this.
you mean that it goes down?
It goes down. Same reasons, it's unusual. But anyway, people go. And I mean, I don't mind changing my view of some as an art. Like if I don't put down, you can cover.
I want to, but my thing, yeah, you guys go for my. That's short.
But
Oh no, it's good notes. I don't actually reading.
I mean, I can send you someone.
We have one in the door, you guys like that.
So at least you can see.
I wouldn't be surprised if
Solid angle doesn't really make sense.
Yeah.
I don't know if you noticed, but it's like there's like a half second delay.
Someone scores a goal, you cheer, like, half a second later, hear it first.
This one, I always get the elite streams from watching, and my friends are watching at the same time, and they're like, I'm like, no, don't take.
Okay, so let's start. This Pastor will give a second lecture on final temperature bootstrap. Please.
Okay, thank you very much, Jörg. It's me again. So I'm going to be together for the last hour, the bitter end today. I'm going to be extending the discussion from this morning. So a very quick summary to go from DS back to this bootstrap ideas. What we discussed was the general setup of the conformal bootstrap program. So we started with some basic facts about conformal field theory, conformal symmetry, how that constrains the observables in a CFT, which are correlation functions of local operators, although you can have also other kinds of operators like effect operators and so on. And then how imposing consistency of conformal symmetry on the 4-point function leads to the so-called bootstrap equations or crossing equations. The condition that you can complete the 4-point function into different ways leads to constraints on the CFT data. And the CFT data were the operator dimensions, OP, coefficients, and that's it. And then towards the end, I said that there is a nice numerical approach to trying to solve the bootstrap equation, the crossing equation, where instead of solving the direct problem, you map the problem to a dual problem, and you scan instead over the space of linear functionals in a particular way. And one of the things that I wrote, see, this morning, and here we have some zero. So this was the difference of two conformal blocks. These were the OP coefficients for a correlation function of 4 identical scalars. And one of the things that we saw was that it was very crucial for the application of the linear functional method when I applied the linear functional these differences of conformal blocks for this thing here to be positive. This came from unitarity, but you can already see that if I have a CFT that is non-unitary and entertain such a possibility, then this whole approach goes out of the window and I can no longer get these bounds on, for example, the CFT data. So there are many examples where this positivity argument does not hold. Examples of CFTs with boundaries, CFTs with defects. The one that I would like to approach right now is CFTs at finite temperature. And to sort of tie in with the theme of this workshop, the reason we care about this in string theory, one of the reasons is that these are dual black holes in ADS. So I would like to consider, so I spoke about the bootstrap program this morning. And this afternoon, I'm going to talk first about finite temperature, see if this is a finite temperature, how you set up the bootstrap in this particular case. And then I'll have a disconnected part about deep neural networks. So once again, I encourage questions. It's late, we're tired. One way not to fall asleep is to ask questions, both for you and for me. And then I'm actually, in the second part, we'll see who has more questions, the old people or the young people, and we'll start talking about machine learning, because some of you might have thought about machine learning more than some of the more senior members of this audience. Good. So safety at finite temperature. So what I would like to do is consider CFT at a where my observables, my correlations functions are going to be evaluated at the thermal equilibrium. One way of understanding this is, instead of having my CFT, which was Euclidean CFT, in flat space, so in RD, becomes CFT on RD minus 1 times this 1 with some radius beta. Okay, so you might have seen there is a way of computing, let's say, correlation functions and partition functions for theories by expressing them in terms of a path integral language. When you've got finite temperature, this translates into a path integral where fields, let's say bosonic fields, are periodic around a Euclideanized time direction. So you can think of your space-time in this case as being a cylinder where there is a radius proportional to beta. Beta is proportional to the inverse temperature for those theories. So that's how this kind of temperature arises. It's proportional to the inverse radius of that Euclideanized circle. And then you have here are your, is a cartoon of the remaining directions of your space-time. Okay, so because I'm going to be working with scalar fields in this space, bosonic fields have to obey a periodicity condition. So I impose that my fields, which are evaluated at, let's say, the point tau plus beta, modulo factors of 2 pi, have to be the same as go around an integer number of times, should get back the same value for my scalar fields. Okay, so this is the more or less the setup. So what changes in my discussion about symmetries and the bootstrap from the theory at 0 temperature? So you see, if beta here, which is the radius, goes to infinity, this corresponds to a 0 temperature CFT. So I'll use this nomenclature. From now on, 0 temperature CFT is what we did this morning. Finite temperature CFT is when you have this. Okay, so what changes in that case? So at finite temperature, locally the structure of symmetries is the same, but sort of globally they are not. So you have reduced symmetry. So for example, your conformal symmetry, which we had at the very beginning, which in fact is isomorphic to SOD plus 1, 1 in Euclidean space, gets broken down to rotations in RD-1 times some U1 associated with this time direction. There also is a time reversal symmetry for the thermal state. Reversal symmetry or tau. A very big difference between the 0 temperature case and the finite temperature case is that 1-point functions, which we said this morning, were identically 0 at 0 temperature for any operator, because conformal invariance, this thing scales with scale transformations, whereas this thing does not have a scale. At finite temperature, so if I compute this 1-point function or a finite temperature CFT. Now there is a scale, and this scale is parameterized by beta. And then I have here some constant. So 1-point functions are non-zero. This coefficient here is known as the thermal 1-point coefficient. And now it's a quantity that we would like to determine in this finite temperature case. Great. The second thing that changes, there's more structure here at lower values of n for my n-point functions, is that my 2-point functions now provide, previously they were completely determined by conformal invariance up to normalization for my operators, and now they have additional structure. So it turns out that I can use this SOD-1 symmetry to reduce the functional dependence of these 2-point functions, let's say of phi at point 0 and phi at a generic point, to just 2 real variables. So here I depend only on where I am along the circle and 1 radial distance along the remaining flat directions, or Cartesian directions. And this thing I'm going to call G tau x. Okay. So it turns out that this quantity already, if you combine it with the tau goes to minus tau symmetry, and the fact that I have to have this periodicity property on my scalar fields, as under tau goes to beta plus tau, gives rise to a condition which is non-trivial and is known as the KMS condition. KMS stands for Kubo, Martin, and Schwinger. And this condition says that G, evaluated at this point, has to be the same. So you can sort of do some massaging. It's not completely obvious, but you can write it in this form. But it's a non-trivial condition on this thermal 2-point function. Okay. So this G is my thermal 2-point function. Previously at 0 temperature, this was completely determined by conformal symmetry. Now you no longer have this redundancy. There is some non-trivial information captured by the fact that you are on a Euclidean circle. Okay, so this is the KMS condition. By the way, everything that I'm writing here is in the notes that I showed you this morning, and actually even more. Very good. So now, I can rewrite this equation for questions if something doesn't make sense. It's not because it's trivial, it's probably because I explained it badly, because now there's going to be more things that we start to have to kind of sweep under the rug. Okay, so now let's do something interesting here. First of all, I can call this thing, I'm going to call sigma. And then I'm going to make a change of variables and define some coordinates z, which are tau plus I sigma. And I have also the complex conjugate.
If I can ask.
Yes, please.
It requires a bit of explanation, no? You don't just state this without explaining it.
What do you mean? So this condition here?
Yeah, because it's.
So it's a combination.
Usually we would have just periodicity.
We have periodicity.
Or an expectation value of the 2-point function.
Yes, it's combined with this, the symmetry of the thermal equilibrium state.
Contour with the complex contour. It goes back in time.
I have not sort of, I'm not going to go into these details in this case.
Because it's the lower part of the contour goes in the opposite direction. So, and Some trivial condition.
It is not a trivial condition. I
But
completely
the other one is trivial.
The periodicity is very simple. I completely agree.
That's why
I completely agree.
maybe for students it could be good to have it. Explain.
I have not sort of don't have this in my notes. We can discuss it later maybe and see, what the best pedagogical way is to introduce that. Okay, so if we introduce these complex variables, we can rewrite this equation here as follows. And this rewriting of the KMS condition looks very much like, at least at the functional level. Okay, so it looks like the crossing equation. So in fact, this equation here does not come from the 4-point function. It doesn't come from using the OPE in a particular way, but still it kind of looks similar to the way that we wrote the crossing equation. And in fact, it originally appeared in a paper by Cheryl Shok and Kyriakos Papadodimas, where they discussed the possibility of maybe using this equation in analogy with what happens in the zero temperature bootstrap to bootstrap finite temperature CFTs. Say again? I did set beta to 1. Thank you very much. Yes. So thank you for that. Sorry. Yeah, thank you. Okay, good. So already we're seeing that there is some equation which could play the role of the crossing equation at zero temperature. So now, how can we make use of this to set up a bootstrap problem like the one that we had at zero temperature? First, we'll see what happens to the OPE. We introduce the operator product expansion as a way of rewriting two operators, in certain points close together in terms of the sum of an infinite set of operators. What happens to this in the case of finite temperature? So I'm going to rewrite exactly what I wrote this morning, but I'm going to present here the right-hand side in a slightly different way. So this morning we said that I could have here a sum over a set of X, like over a set of primaries for my theory. And then if I stick this in a correlation function, I would have expectation values of 1 point. So this operator, this is a 1-point function at zero temperature, it is 0. But at finite temperature now, I can have expectation values that are not 0. Now, I should state here that it's the expectation values only of primaries that are not 0, because these guys are constants. If I have descendants, which are obtained by acting with derivatives on the primaries, I end up having derivatives of this constant, and I get 0 once again. So what I would like to do is to rewrite this expression by including some constants, multiplying some spin j primaries plus descendants. And the reason I want to do that is that now if I compute the expectation value of this quantity on the left-hand side and the expectation value of this quantity on the right-hand side, these things are going to give you a non-zero contribution because of the fact that I'm at finite temperature. And with some work, once again, I'm not going to do this here, you can show that the contraction of these indices with the various structures, let's say the invariance that you can construct out of being in d-1 dimensions, allows you to write these 2-point functions. Maybe I should put that. Well, Z is a partner. You know what? I'm going to introduce one more change of variables, and then I'll write this And so I want you to write this in polar form. Then I can write that my 2-point function as a function of z bar is given in terms of the sum of these Oj's. And then here I get delta J. Some functions known as Gegenbaur polynomials.
Let's just maybe be
Yes.
the pen.
Yeah, I don't know if the other one is much better, so. This much better. So what am I saying here? That there is if I compute the thermal version of the operator product, I use the operator product expansion in a finite temperature CFT, I can expand the 2-point function in terms of a set of thermal blocks. So this thing here I can treat as a thermal block loosely, where I've got a bunch of coefficients. These are some coefficients which I can write explicitly. Times in this case now have a nice, instead of previously we had conformal blocks, here we have a nice factorized expression where we have a dependence on this W, so the kind of the phase, if you wish, in this case, and the radius completely separate from each other. So these guys here are known as Gegenbaur polynomials. Gegenbaur polynomials. They are known in closed form. Kind of provided a generating function for these things at the end of the notes. And let me write a couple more things.
What's
Yeah.
that? Thermal block?
Which one?
So in C, yeah.
That's a new. I was about to write this. New is just a dimension dependent constant. It's d-2 vector. Okay. And these coefficients here, once again, depend on some known quantities. So I can write my A delta J and on the 2-point function coefficients, the 3-point function coefficients, the normalization, the thermal 1-point functions, and some constants, which are depending on the spin. This is the Pochhammer symbol. Okay, it's a bunch of constants. The important bit is that these quantities are dependent exclusively on the 3-point function coefficients for the theory at 0 temperature. This normalization, okay, which you can set, and these 1-point function coefficients that we discussed at the very beginning, which are thermal 1.5 coefficients. Coefficients, so the OBE coefficients, the 0 temperature theory, and the other stuff is a bunch of constants. Okay? But we can pin them down exactly.
So these thermal 1-point functions, is that independent dynamical data?
Correct. Is the thing that is different. And exactly as Sam is anticipating, the point of using this set of equations as non-trivial constraints on your CFD data. What are your CFD data now? Is everything you had before, the Fs, the deltas, Js, but now also it includes this new dynamical data. And in fact, the phrasing of the bootstrap problem at finite temperature, at finite T, makes the assumption that you assume that the zero temperature safety data is known. So we assume that we have solved the theory at zero temperature, and we're trying to solve for these B zeros through these A's of what I call delta G. Yeah. Any question? So once again, we take the theory, put the finite temperature. There is a condition who plays the role of the crossing equation already at the level of thermal 2-point functions. You don't have to go as high as 4-point functions. And then you end up expanding these 2-point functions in terms of this sort of thermal P. There is a set of coefficients, once again, which you can express in terms of this quantity, and assuming that you know this and deltas and j's, you need to determine these thermal compound function coefficients.
Is the coefficient A vanishing if J is 0?
Is the coefficient? Excellent question. Thank you. The experienced eye of a supervisor. This is how you. Thank you.
Do those polynomials satisfy math properties?
They do satisfy some orthogonality conditions. That's right.
Would it be possible to get the the CFD data from a zero temperature from this crossing equation?
I mean, you need more information, but yeah.
Just this crossing equation.
Say again?
Just from this somehow bootstrap equation, would it be possible to determine the zero sensitivity?
All of them?
Like the spectrum. And the spectrum showing up there in the OPE.
Yeah, usually people do it the other way around, but I think maybe you can do a combined thing where you know.
But I don't want to look at 4-point functions. I just want to look at 2-point functions will be possible.
In principle, I don't see why not.
It looks like an inverse Laplace transform problem.
Mm-hmm. I don't know how constrained you'd be. So first of all, in principle, yes. Now practically, doing it is probably quite hard, right? And we'll see that all the numerical approaches that, for example, people use are not applying, and this is what I'm going to get to just now. So, okay, so this is an interesting case, but why is it different? And why is the application of the numerical methods that I discussed at the end of the previous lecture not applicable in this case? Because previously I had that the coefficients multiplying my proper conformal blocks were manifestly positive, and I could use the linear functional method, and then I can apply these linear programming approaches and semi-definite programming and so on. In this particular case, however, there's no guarantee that this quantity over here is going to be positive. Not necessarily positive. That is a problem. That is a problem for the application of the linear functional method. Because you can have whatever sign you need for this, and so on. So this motivates the trying to attack this problem attacking the primal bootstrap equation. Not trying to find these linear functionals, but trying to solve the original equation directly. And I will, this is going to be the topic of my talk tomorrow, how we're going to try and do that and why. Now, already you might be asking a question. If you assume that you know the spectrum, so you know the dimensions, and if you try to optimize this, the only thing that an optimizer sees is this quantity. So if you know the dimensions, for example, the only thing you need to determine is these coefficients. They appear linearly. It's a linear regression problem, so what's the big deal? But the big deal is that this the convergence of this OPE is not very fast in the space of these two real parameters. And if you want to put this equation on a computer, you need to kind of truncate. I mean, there's various ways of doing it. If you want to do it directly, one idea would be to just truncate here the sum to some finite number of operators being included. And that doesn't work very well. So because the convergence of the OP is not very fast, you do not, if you do this very harsh truncation, you do not approximate this KMS condition properly. You do not solve the equation. So what I'm going to be discussing tomorrow is a way of trying to solve this problem without cutting off any operator and trying to model exactly the infinite tower of operators that appear in this term of auto expansion. Good. So this is part one. And for part two, well, there's a part 1.5 now. So this is one thing, you can park it for tomorrow. What I'm going to try and do is solve this equation without performing any approximation over this sum. I will assume I know the zero temperature data, and I will tell you how to model this using various tools, including dispersion relations coming from the Lorentzian inversion formula and neural networks. Part 1.5 is to discuss some interesting. Yeah.
If you have a theory which simple theory that has only a finite number of primaries, then I guess all this just works.
So you can make assumptions. You mean if you make some certain assumption about the spectrum of your theory?
Then you don't have to worry about convergence, I guess.
Yeah, I mean there you can probably write the sum out explicitly, right?
So your focus is more like four-dimensional theory than Young-Mills and these
things. Right, exactly. Okay, so one thing to keep in mind for tomorrow. The kind of half thing that I would like to discuss now that will also appear tomorrow is a concept known as generalized free fields. Generalized fields. So since I'm talking about scalar fields, the scalar field in D dimensions satisfies the three-wave equation. This also gives us information about the dimension of this scalar field as D minus 2 over 2, and also have a 2-point function of this at zero temperature. So let's go back to zero temperature. 1 over x to the d. So this is a standard free scalar field in the dimensions. But you can have a notion of a generalized free field. Generalized free field is a field whose correlators factorize in the same way into sort of sums of so I guess sums of products of 2-point functions in the same way as you get for a free field. Its 2-point function is given as again at zero temperature in the same way as above, but your delta phi is arbitrary. So the dimensions of the generalized free fields are not the ones you get for a free scalar field in the dimensions, which comes from having a Lagrangian. It can, you can have it also in non-Lagrangian contexts. These generalized free fields appear actually in ADS-CFT. So in ADS-CFT, these are dual to free scalars propagating in ADS with mass m squared is delta phi. Phi is d. Okay, so we have this notion of generalized free field. Yes, Gary.
So do they have, they don't necessarily have to satisfy this unitarity bound, these generalized free fields?
They do not. Unitary theories, they do. Should be 2 delta phi. You're right, actually. Thank you. Okay, so why do I care about these generalized free fields? I care about them because they have, you can solve the 2-point function exactly, even in the context of finite temperature. And in fact, in order for me to do that, let me tell you a little bit about some interesting composites that I can build out of these generalized free fields, which go under the name of double twist operators. So these double twist operators are what you get in the OPE of two of these generalized free fields, phi phi. Only the identity operator and GFFs here. So how do I define these fields? These fields are this composite labeled by N and L. These are proportional to what you can build out of starting with two of these generalized free fields and then sprinkling among them a bunch of derivative squares or boxes, n of them, and then new one, new 2L single derivatives. So in this particular case, instead of using J, I'm using 2L. So 2L equals J. Because I'm working with scalars, only even spin objects appear in the OP phi and phi. The dimensions of these double twist operators are 2 times delta phi here, plus 2 times n from the number of boxes, plus 2L, the number of single derivatives. So I can create an infinite number of these composites. And this is interesting and informative because I can write down schematically the thermal block expansion of two of these generalized free fields. And then what I get here is essentially the identity operator plus these double twist guys. Why do we call them double twist? The twist usually is given by the symbol tau, is delta minus J, so it's the dimension minus the spin. The spin here is 2L, so for n equals 0, tau is 2 delta phi, so they have double the twist of the generalized free field that you construct them with. Okay, so my point is that if I know what appears in the OP of phi and phi for these generalized free fields, then if I write the thermal block expansion of my generalized free field, I can compare it to the exact results that I know for this theory. So first of all, let's go to finite temperature. Okay, running out of pens. So at finite temperature, so T goes to 0. The 2-point function, thermal 2-point function, can be solved using the method of images. In these code, essentially, you have the 2-point function result that I just erased for the generalized free fields, and then you have an infinite set of copies by going around the thermal circle. So you get an infinite sum going from minus infinity to infinity of the appropriately reparameterized version of the two-form function. R del phi. And this is an exact result. Okay, so this is a straightforward computation. We know the answer for the thermal two-point function exactly. This is a free theory after all. But what I can do is that I can equate what I obtain through this exact method and what I obtain by using the thermal log expansion and compare the two. And we can extract through this process the coefficients A and J that appeared in my thermal block expansion, and it's something concrete. I don't know if there's any point in me writing it. Or some known exactly analytically. Yeah, you can find it in the notes. It's a long expression that involves some Riemann zeta function, the sample counter symbols, and it depends on this N and J. Good. So why do I care about this? Because when I'm going to try and use the approach that I will discuss tomorrow to kind of benchmark this approach, I will use these exact analytic results and for the generalized free field. And since this is the parameter that I try to determine from that contains my thermal one-point function data, getting something that agrees with what I can compute analytically is going to be a good starting point for going to more interesting examples, like, for example, holographic CFTs at large N. Okay, great. So that was the end of point 1.5. And in the last 20 minutes, I'll change gears completely. And I'll talk about some basic of neural networks. So any questions about this before we move on? So once again, finite temperature, KMS condition. The KMS condition plays the role of the crossing equation at zero temperature CFTs. What are the unknown? There are these bunches of coefficients. Thank you very much. So when I am in the context of generalized free fields, I know what I expect to find exactly. I would like to try and use some tools that I will discuss tomorrow to determine those objects. Okay. Is this? And now move on to this final bit. So, which of the young people have played with neural networks? ML. Even epsilonically, 1, 2, and there we go. Which of the old people have played with neural networks? Older. Which of the distinguished members of the audience have played with neural networks? Okay, someone has written papers on that. But okay, it's still a smaller subset of. So I would like to, because I will talk about neural networks tomorrow. I thought it might be nice to give some very basic introduction of the most vanilla architecture that appears for neural networks and machine learning and what the process is for training such a network. So we're interested in neural networks as function approximators. And in particular, I'm interested in the architecture known as a multi-layer perceptron. Multi-layer perceptron. Perceptron. MLP. So what is a multi-layer perceptron? The function that takes some input, right? So this can be some n-dimensional space, and n gives you some n out dimensional output. Okay? So it receives an input, it provides out a function, valued in the reals. And maybe let's draw the picture first, and then we can see how everything. Yeah, so this is a schematic picture. Maybe I should not draw too many nodes because then I'm going to get myself in trouble. And these bits over here are called neurons. All these dots are called neurons, and the neurons are in a multi-layer perceptron, which is what is called the feed-forward neural network, are comprising a layer. So each of these things is called a layer. And they are connected, or a maximally connected neural network, to all neurons in the next layer, and likewise here. Now, what do we do with this information? Well, I will label each layer. Each layer takes an input vector. The input vector has components corresponding to the values that are entering, I guess that are labeled by these neurons. Input here is some H vector at position L. So this is the input layer, position 0, position 1, position 2, position 3. I should maybe say that the first thing is called the input layer. The last layer is called the output layer. And everything in between, in this case, 2, are called hidden layers. And hidden layers, actually, if you've got more than one hidden layer, you're kind of qualified to call your neural network deep. And have many hidden layers, so it can be a very deep neural network. So each layer takes input, so it takes a bunch of vectors and converts it to an output at the next layer. That's one. How does that happen? So the values of the following layer are given by the following formula. So I have a set of matrices W acting on the values of my network at the previous layer. And then I also have something known as so these things are called weights. And then I've got a bunch of vectors that I can use to shift, literally translate the values that I had in my previous layer after being acted upon by the weights, which are called biases. Because what I'm trying to do here is approximate a function. The fact that I have biases allows me to, produce functions that do not have to pass necessarily through the origin. And this guy here is a function which is called an activation function. My activation function is usually a nonlinear function. It's important. So it can be, for example, hyperbolic tangent, it can be a sigmoid function, it can be something known as a rectified linear unit, which is the max 0 and x, so it goes like this. Sometimes people call this the hinge function. So it looks like a door hinge. And what this allows me to do is to approximate any nonlinear function to arbitrary accuracy. So there is a theorem known as the universal approximation theorem. And the universal approximation theorem says that if you have a multi-layer perceptron architecture with at least one hidden layer, you can approximate to arbitrary accuracy any function. And for that, it's crucial that you have a nonlinear activation function acting on these values. Okay, so we can approximate any function to arbitrary accuracy. Okay, very good. So
hidden layer need to be of a specific size.
Okay, so very good. So how good your approximation is depends on how many nodes you have, how many neurons you have in your hidden layer. You can achieve, certain better approximations with more, for example, neurons, or maybe you can have more layers and then have more layers and fewer neurons, and then you can achieve. So it's a bit of an experimental.
So, sorry, just to make the connection between the picture and the formula. So
Yeah.
the number of points is related to the dimension of the vector.
Precisely.
So each point is one element, one entry of the vector.
Correct. And then this thing is, what is it? This kind of input times output as a matrix.
Okay.
And then this has also the same dimensionality as the, as
the
L+1, correct, yes.
So omega is rectangular.
So this is W, it's rectangular, correct, exactly. I mean, if you don't have the same number of neurons for each layer, it can be rectangular. Correct. Now, these weights and biases are known as the parameters of your neural network. These are my
Just one question. This
is
sigma is acting
on all the
L
universally on, yeah, exactly.
One by
one, correct. And it's the same for all of them. Yeah, so, you know, sigma is not different between layers. It's the same for the whole network. So these things are called the parameters of your neural network. So sometimes people all them combine them together into this theta, W's, and B's. These are the things that are trained during the training phase. So what happens during the training phase is that, how do I use this? Well, usually, or at least in the original implementation of neural networks, I start with a collection of data. Okay. So we have some data. Let's say that my data set is some inputs and some outputs, which is my truth. Bless you. And then I try to use this network to approximate, to come out with a function that reduces to these points, to these outputs when you consider these inputs. Okay. In order for me to do that, I need to define something that is called a loss function. It's an optimization problem. And this loss function can be many things. So depending on how you choose the loss function, you can get many varying results of varying quality. One standard thing is the mean squared error loss function. Let's say you've got n data points, and so you consider the mean squared error. Okay, so these are the outputs. You construct this function, let's say, for some initialization of your weights and biases, theta. You get an output, you evaluate this output at point xi, and then you go and see how close this output xi is to the set of data that you're training on. And you're going to get some answer. Obviously, if you got 0, then you perfectly are modeling your data. But if it's not 0, then you kind of go back and update the parameters that define your neural network, these W's and these B's, to change the functions so that the next time you're actually closer to the things that you want to evaluate. So that means that at each step, there is an update of these parameters. So this is how computer scientists usually write these updates. The most standard thing that you can do is follow some kind of Newtonian optimization, some gradient descent, where you look at how this loss function changes as a function of changing your variables. Here you have some step, something controlling the step, which is called the learning rate. And then you update your weights with these values. So, you know, the steeper the descent, or the bigger the derivative, maybe I should say differently. So the update of the parameters follows the, in this particular case, you know, the steepest descent. Obviously, if you have a set of a search space which is very high dimensional, can have many local minima, you don't have a convex problem, you can get stuck in many local minima. So there is better ways of performing this step. There is, for example, a method which is called ADAM, or adaptive momentum estimates, and there, you know, you can come up with more baroque versions of this, where you have some momentum, so you're averaging over the, you know, previous steps. If you're kind of, you know, going down very quickly, you gain some momentum, so you can escape from local minima. or because as you have increasingly high dimensional search spaces, it is known that it's not more local minima that you get, but you get more flat directions. So you can get trapped in a flat direction in a certain bit, while you can have very steep directions in some others. So you want to basically, try to escape from these flat directions. And this Adam optimizer is, I would say, the kind of canonical choice in this line of business. For you to get a sense of how big this community is, the Adam paper came in 2014. Guess how many citations it has? 10,000. So for comparison, the AD/CFT paper has 20,000 citations. 230,000 citations. So these are the people who cite it. Very good. Okay, so let me close by saying, how does this start closing? How does this relate to what we want to do in physics? Because the one word that I used here, which is a dirty word, unfortunately for us, is this. In theoretical physics, we usually, unfortunately, do not have a lot of data. So how can we use any of this? The answer is that there is a variant that people use in machine learning of a neural network called a physics-informed neural network. This thing goes under the acronym of a PIN. This is nothing, there's nothing physics about it, actually, unfortunately. You just supplement this loss, which depends on data, with another loss, L physics. I'm keeping the word physics because that's what engineers call it. And essentially what this physics loss is doing is trying to enforce a constraint that you know your functions should satisfy. So let's say that if you have a function that obeys, or a differential equation, something that is obeyed by like your function to obey that, you can come up with an additional physics loss, and where you just find some way of imposing this constraint for the output functions that you produce through your neural network. So then you're training both using data or using and having the final function that comes out obey certain constraints. This is how people use it in sort of machine learning contexts. But for us, if we don't have any data, it's absolutely fine to ignore this bit and just have some constraint that we would like to determine. So in the end, how are we going to use these machine learning tools and these neural network tools? We would like to try and approximate some function which obeys a constraint, for example, the thermal bootstrap constraint in my case, by feeding it through a neural network. And you'll see exactly what kind of functions I will want to approximate tomorrow and how they fit in the context of this thermal block expansion that I discussed earlier on. Let me see. Let's finish 4 minutes early. And then if people want to have a look, if the students want to have a look at what I'm going to be discussing tomorrow so that they can follow, again, in the notes, I have a kind of a bullet points of the main steps.
During the training phase, when will we know the training is complete or almost complete?
You do not. I mean, you mean what's the stopping criterion?
It's
up to you. You set a number of epochs. So you say, update 3,000 times, something like that.
Okay, does it approach asymptotically or?
So you can see, for example, what the loss is doing, right? So you can measure what happens to this loss, and if you've done things properly, this is kind of highly stochastic. Sometimes it's kind of plateaus, and then at that point you say, okay, my training has been I've done what I wanted it to do. At least that's how people do it in practice.
The second question is, if you think of this as some kind of manifold, can there be a manifold with no global minimum or something. Is that possible?
I mean, there has to be some global minimum, but I guess, is it very hard to find is what is your question. So, you know, you can have oh, absolutely. You know, if you have high dimensionality of your search space, you can have like a kind of a spin glassy kind of behavior where, you know, the minima look like this. I mean, good luck finding. I mean, but the question is there a difference, for example, between this minimum in practice? And there's papers in computer science by Jan LeCun saying that, you know, if you land here, it's kind of roughly as good as landing there. So, but yeah, I mean, these are the kinds of problems that you have in this case. Yeah, there's one thing that I didn't say is that, you know, we have the parameters of the neural network, but we also have these kinds of additional parameters that are not updated during the training stages. And these things are called hyperparameters. So if you hear this word, for example, this learning rate is a hyperparameter. And these hyperparameters are the things that people sometimes tune and they say, okay, I do a tuning because my training also depends on the correct choice of this guy. If this guy is like too big, you could be trying to, you know, track this minimum, I don't know, and, you know, escape from it and lose it, right? If it's too small, it's going to take a very long time for me to converge to the global minimum. So there are, I think, indeed people, I mean, now all these are done automatically. But let's say 5-6 years ago, there were people who would start their morning by starting a big Excel spreadsheet. Eta is 1, run. Eta is 2, run. You can see which one is better. But now these are automated.
Any other questions?
Sorry, you mentioned something briefly before, maybe I missed it. So what is the strategy to escape false local minima? Precisely this.
So the strategy to escape is that you have this kind of, you know, an enhancement of this update rule, where you can have momentum, if you wish. I mean, along.
Also introduce a stochastic variable, like a random variable.
You could do that, but this approach here, yeah, that's two things. I think it introduces an adaptive learning rate, so it kind of tells you how big or small the for each of these parameters the update should be, and then it also has momentum, kind of controls how much you update by taking an average of the previous ones. So this seems like it's kind of escaping lots of these local. So these optimization landscapes are highly non-convex with many, and it seems that this kind of algorithm works. And I don't think that there is a proper understanding theoretically why it works so well. You know, because when I should say that the number of parameters we're talking about here, if you look at the LLMs that we use are not fit for neural networks, but the small ones have billions of parameters. 8 billion parameters. And the big ones like ChatGPT probably have hundreds of billions of parameters. So optimizing in that space is not a simple thing to do. And somehow these tools, these algorithms work very well.
More questions?
What if like flat?
Completely in everywhere? I think it's good.
How do you know it's not?
How do you know that there is any minimum at all?
Have some flat directions, right?
I mean, you would probably see it from the loss, right? I mean, so if you have you could have flat directions, and somehow one of the points of adapting these things is to escape flat directions. So you say if you're in a flat direction, you make this thing bigger to try and escape from these flat directions. Yeah, but think of this as a very high dimensional, you know, if you've got like, I don't know, 8 billion parameters, you're not going to have like 8 billion parameters where it's flat. You'll have, you know, one where it's flat, and then the other ones are going to be like this, going to have some, it's saddles mostly that you get. And you can escape these saddles, it looks like.
Yeah.